Singhal from USA. We have Professor Chandradeep Tandon from Amethi University, Noida. We have Dr. Gagan Kumar from IIT Guwahati, and many more for tomorrow's session. As we have Professor Poonam Tandon from Lucknow University, Lucknow, and we have for tomorrow Dr. Mohit Kumar and Dr. Nagendra Kaushik and Professor Yuha Choi from South Korea. Esteemed participants from various states and UTs of India, chairperson of different technical sessions of this webinar, as we have Professor Lokendra Kumar from Allahabad University, Prayagraj. We have Professor Sunil Kumar Kha from JUIT Solan, Himachal Pradesh. We have Professor Sanjeev Kumar from Rajiv Gandhi Central University, Itanagar, Arunachal Pradesh. We have Dr. Shobna Chaudhary from CSIR NISCARE, New Delhi, and dear students. On behalf of organizing committee of this international webinar, I, Birpal Singh, head Department of Physics of this university, take this opportunity with immense pleasure and honor to welcome you all to today international webinar on perspective of interdisciplinary research in science and technology in present scenario. The Department of Physics in the historical city of Meerut is one of the oldest department of this university with outstanding research work. The department provides a state-of-the-art learning environment of the students from all over the nation. And the department produce up to now many renowned scientists, academicians, professors, administrators who are serving at the reputed institutions at national and international level. In past, we used to organize several national and international conferences, workshops, and training programs. Now, this e-conference is the first ever event of its kind organized by Department of Physics as online conference. This international e-conference is aimed at achieving cherished goal of bringing the expertise and novelty of research together to navigate the human race in COVID-19 pandemic. This vibrant e-platform of the webinar, I'm sure, would be a milestone in the interdisciplinary research in science and technology. I personally believe that the only science and technology have the capability to deal with the never before experienced phenomena as you are seeing nowadays COVID-19 by exploring new dimensions of interdisciplinary science and technology in future. During the course of the webinar, the leading scholars of high caliber across the globe will be sharing their innovative ideas to our participants. And at last, I would like to conclude my welcome address quoting by a pertinent Sanskrit phrase from Maha Upanishad, Vasudev Kutumbakam. The word is one family. And being member of this one family, we, as famous British poet Alfred Tennyson says, have to strive, to seek, to find, not to yield. I wish you all a very engaging and fruitful meeting for this webinar. And thank you very much. And now I request Professor Anil Kumar Malik, who is organizing secretary of this international webinar, for further proceeding of this inaugural function of the webinar. Thank you all.
Thank you very much, Professor Virpal Singh. Am I audible? Yeah. So good morning, Professor Ankit Taneja ji, Honorable Vice Chancellor, Choi Charan Singh University, Meerut, Professor Krishnalal, Chief Guest of this session, Professor Vimala Vai, Pro Vice Chancellor, CCS University, Meerut, Professor M.K. Gupta, Dean Science, CCS University, Meerut, Professor S.P. Khare, founder of our department, Professor P.K. Gupta, Department of Plant Breeding and Genetics, an eminent agriculture scientist, Professor Virpal Singh, convener of this webinar and head of the department, CCS University, Meerut. Invited speakers, distinguished invited guests, delegates, and my dear colleagues. Problems always bring with some opportunities. The COVID-19 pandemic has brought us to a new sagacity towards ingenious efforts with the use of available advanced technologies. Keeping this in our view, we thought that the global scientific community must continue to play an active role in the science and technology innovations and must share their expertise among the academic fraternity across the globe in the area of interdisciplinary science for the betterment of the humanity, even during this difficult time. With this view, during this lockdown and social distancing period, Department of Physics, Chaudhry Charan Singh University, Meerut, with the vibrant leadership of our Honorable Vice Chancellor, decided to provide an e-platform to the scientific community for sharing their ideas and research expertise in the form of two-day webinar on the topic Perspective of Interdisciplinary Research in Science and Technology in the Present Scenario. This webinar will cover broad areas of interdisciplinary sciences like plasma science, atmospheric sciences, nanotechnology, artificial intelligence, chemical sciences, life sciences, and agriculture sciences. We opened registration link for this webinar on May 10, 2020 and received overwhelming response from the participants of different disciplines of the science and technology. We received around about 800 registrations in 48 hours from all over the country. We received abstracts from IITs, AIMS, New Delhi, DRDO, NITs, and also from prominent Indian universities like BHU, Allahabad University, Hyderabad University, Delhi University, Kolkata University, Lucknow University, and many more. More than 20 speakers from prominent institutes in India, as already Professor Birpal has mentioned, like Dr. Sanjeev Srivastava from ISC Bangalore, Dr. Mukesh Ranjan from IPR Gandhinagar, Professor Ramesh Chandra from IIT Roorkee, Professor Gagan Kumar from IIT Guwahati, Dr. R.S. Davas from NPL New Delhi, Professor Poonam Tandon from Lucknow University, Professor A.B. Yadav from Allahabad University, Professor Chandradeep Tandon from MIT University, and outside India, like Professor Dinu from UK, Professor Anton from Slovenia, Dr. Vikas Rana from Germany, Dr. Rahul Singhal from USA, Dr. Mohit Kumar, Professor Nagendra Kaushik, and Professor Eun Ha Choi from South Korea have consented to share their ideas. This webinar has 8 sessions, including one each for inaugural and valedictory. 2 sessions are for invited talks and 2 each for oral and poster presentations. I believe that you will enjoy all the sessions and bring home some new knowledge, new and fruitful knowledge. Thank you. Now, I would like to introduce Professor Kishan Lal, our chief guest of today's session, or this session. It is my pleasure to introduce our keynote speaker and chief guest, Professor Kishan Lal, an erudite academician and notable scholar. Due to time constraints, it is difficult to tell about his all professional and academic achievements. Professor Lal has served in the capacity of president of many prestigious institutions like co-chair, AIP Global Network of Science and Academies, President Association of Academies of Societies of Science and Science in Asia, former President International Science Academy, New Delhi, former Director, National Physical Laboratory, New Delhi, India. He has published more than 100 research papers, 22 rated papers in research journals of very high repute, and he has earned 7 patents and edited 9 books. We are deeply indebted to Professor Lal for his unconditional support and motivation. Thank you, sir. Now I invite you to bless us, Professor Kishan Lal. Kishan Lal, sir.
माइक सर, माइक बंद है इनका अभी।
अभी ठीक है? अभी आ रहा है?
अब आ रहा है।
आ रहा है कि नहीं? I have, can you hear me?
Yes, sir.
Sir, we can hear you.
Okay. So thank you, Professor Birpal Singh, to begin with, because he is always there to have a contact and also to get me involved in many activities, and Dr. Malik. But to begin with, I must thank and admire Professor Taneja, the Vice Chancellor, Pro-Vice Chancellor, for their initiatives to activate the faculty and research scholars to deliberate on issues which are of contemporary importance, which are having attention of the global scientific people and also others, even including the political leadership, how to deal with one of this greatest challenge of at least this century, the COVID-19. So I thank, and also I noted Professor Khare is there. I have remembered him for a long time, and I can't resist mentioning I'm a product of Meerut College, and at that time there was no university, but Meerut College was the one, and we had many distinguished people there. Professor Roop Kishore, a student of C.V. Raman. Because of him, twice Raman Saab came to Meerut, and many other. I mean, I can just mention for students, when we were students, Professor D.S. Kothari gave us extension lecture for 3 days at Meerut. So Meerut has a long tradition, and Dr. Birpal Singh and others are keeping it up, and I'm very glad about that. Now coming to the present topic of your research on challenges in interdisciplinary research. One of the key challenges to deal with this great challenge before whole humanity, not only India, but entire world, the virus COVID-19, which got mutated, it got many transformations starting from bats, humans, and now troubling entire world. India is also quite a bit affected, but our government has taken wise steps, strong steps, and that has helped in some ways to keep it in a slightly lower key. It is not over, it is there, it is challenging every day. The numbers are increasing, but I was looking at the numbers. They now about 11, 12 days it takes to double the numbers, but numbers are increasing. So this means that we have to be very careful with ourselves, with our community, our family, friends, that how to deal with it. But what I want to say is that interdisciplinary nature of science has been there for more than 100 years. Now one of the key question is, what is this virus? What is this virus? Can we understand something about this virus? So these are some of the things, and what is our method of understanding some species like viruses and other biological systems? This is one of the challenge we always face. Now the question is, can only the life scientist people can throw light on this? Can they know it, everything? Do we need other disciplines, maybe chemistry people, maybe physics people? So to give an example, I take the example of diffraction of X-rays, because this also is playing already a role in revealing what is this virus all about. In a simple language, if I may say, the virus is basically a protein. It has a series of RNA, not one RNA, series of RNA, and it has the great characteristics. It covers itself with a fat molecule or fat layer of fat molecules. And because of this, it can interact very easily with the human body at different levels and so on. Now, if we go back a little bit, one wants to understand the structure. Structure means how atoms or molecules are organized within this virus. How this whole process is started. You have a lot of participants, some of them may be students. So I'll start in a very from the very beginning in a simplistic manner. Most of you would recall that it was in 1912, 108 years ago, that in Munich, Max von Laue, with two of his collaborators, he discovered diffraction of X-rays. He took a zinc blende crystal, which is a four-fold cubic crystal, and with a picture, he showed a four-fold symmetry of atomic arrangement inside the crystal. The spots were arranged in the photograph he showed, the spots were arranged in a four-fold symmetry. 1912, he did not yet publish a paper. There is a Bavarian Academy of Science. Each state in Germany has a Academy of Science. In fact, right now I have very close relation with the German National Science Academy, Leopoldina, which is in Hase, not in Munich. So what he did, that he published a report or a short note in the proceeding of the Academy 1912, and next year got the Nobel Prize. The impact was so large. And now from this, he only showed that diffraction can take place. Within a year, the Cambridge group of father and son team of Braggs, they took very good example, alkali halides and diamond crystals, and demonstrated how atoms are organized inside these cubic crystals. This led to great activity, particularly in physics. First 10, 15 years, the domination was physics. Gradually, the chemist came into the picture. Actually, now sometimes we say the physicists are not so much active as the chemist first took over. And the chemists took, particularly the Cambridge group, they took upon themselves whether they can solve biological molecules. And the first great success was with the of DNA, and thereafter it was not waiting. Thereafter it is not, nobody worried, and now many molecules, many these biological systems, molecules, and entities, they have been investigated. Several Nobel Prizes have been won. And in a simple terms, I can say now there are more than 1 million compounds whose structure is known. When I say structure is known, what do I mean by that? To begin with, you have to define which unit cell it has, how many atoms are there, how they are organized, what is the symmetry element, and so on. Now there are about 1 million. We jokingly say now in science, the first phase, we had the physicists dominating because they add into it many interesting things. For example, one of the interesting things out of physics came that when diffraction takes place, the crystal loses its absorption. Crystal becomes more transparent. In fact, the big example is that if you take a thick crystal, which is normally opaque, acts like a screen to block the X-rays, but if you allow it to diffract, it becomes transparent. You can see this is the anomalous transmission X-rays. We have several publications on this, but later we showed all crystal will show, don't have to be thick or thin, only if you have high quality technique. The main thing I'm saying is, then this was the physics. Physics still keeps on doing. On physics side, I will particularly like to emphasize, because CCS University and Birpal Singh and his colleagues have set up laboratories in nanosciences and so on. Therefore, I want to say a few things. It did not stay, not only biological, now we went on decreasing the size of the specimen. We are not worried that it should be a big crystal. We started seeing very thin crystals. One example is graphene. You can have only one layer of carbon atoms, which can also be investigated. But if you look at this, there is a new technique which we perfected at NPL, the reflection of X-rays. X-rays have a peculiar property that when you go to very low, high frequencies or low, small wavelength, the refractive index of the material becomes less than 1. This is very anomalous. A student must think the air and the material, if you see the interface, the air is now denser than the crystal. The crystal becomes rarer, which means, in fact, you can get total external reflection, total external reflection. So these are things which keep on happening. But as I was saying, on the other hand, people took great strides going into the life sciences. Now, I would like to say, still, when you say we have, I will show some recent results on this, on diffraction. But when we say that this is broadly approximate structure known today, but how does it convert into, say, covers itself with a fat molecule or fat system, and then enters the human body and attacks it? These mechanisms are still in the primitive stage. We are not fully, as far as I know, I am not a life scientist, but broadly, this is what being done. This I also would like to say, those of you who are very keen, because as was mentioned in my introduction, there are about 110 national science academies in the world, and they have one organization, we call it Inter-Academy Partnership. In this, I happen to be one of the 2 co-chairs. So we, from time to time, have been also issuing a statement or communiques on different issues. And COVID-19 is one of them. Those of you who are keen, they can look at the website of IAP, Inter-Academy Partnership. There is a signed statement of which I am also a signatory, which covers all the relevant challenges which one is facing today. It's not a question of being a physicist, chemist, or life scientist. It is the overall issue, how to tackle such complicated issues. Similarly, there are other many efforts are there. WHO website has also a lot of this thing. But before I proceed further, I want to show you 1 or 2 structures which have come recently into this thing. Maybe I will use a, perhaps you can see this. Can you see it? Can you see it on your screen?
Yes, sir. Yeah, we can see.
Okay, I will show you 1 or 2 molecules and then explain what is the significance. This is only a couple of months old. Can you see it?
Yes, sir.
Yes,
Yes,
sir.
Okay. Why I put this together? Now the question is, when you know this broad structure, you know also part of this. But this same thing may not happen globally. There will be small variations. And that is where the challenge for everybody, how to correlate with this thing. I may little bit go to material science with your for your attention. In material science, because I'm a material scientist, when you want to see how a material behaves, you have to take care of or to understand 4 components of that material. First is composition, what a material is, which in this case we can say this is a this virus or this virus. Unfortunately, viruses are more difficult, but the other problems in health with antibiotics we can solve. So composition, but everything, you can take silicon, you can take gallium arsenide, you can take a steel, but composition is not strictly as you have specified. It varies slightly. And in India, we are very weak. We have not bothered about a specification. I will come for a moment into that. Then comes purity. Whether you, if you have a silicon, most impurities you would like to do have below around 1 part per billion or even lower. But some you can tolerate up to part per billion. Water is still a problem because in many parts of our country, for example, arsenic in the eastern part is much above the permissible limit as done by WHO. So the purity is very critical. Also in semiconductors, in computer technology. These two, the composition, purity, purely chemistry. Then comes a structure, which is physics. What we describe ideally, for example, silicon, we can say it's a diamond structure, two face-centered cubes interpenetrating into each other. But that is idealistic. That is ideal structure. Now, each structure has defects. The defects can be from a very broad thing, whether a crystal is single or not, boundaries, or low angle bound. Or what we discovered, even very low angle, which did not exist earlier till we went into great detail. But more so, the point defects and their clusters. Now, same thing we sooner or later will have to do with the viruses also. All the viruses that you see with each individual, the specimens come from human beings or bats or wherever you take it. They will all have some differences in their structure as well as the chemical aspects of them. And sooner or later, they have to be brought in if we want to understand. So these are the broad scientific aspect. I know the paper I showed you is only 2 months old and so on. But now the question is, this is the scientific part. When the government is trying to create facilities for treatment of people who are suffering from this problem, the infection of COVID-19, or how they are recovering and so on. One of the simplest method was that we keep each away from each other at a distance of more than a meter so that we don't transmit, because it comes from what you can throw out as small droplets from your breathing and otherwise. That is why all of us are putting masks and so on. But now the challenge before scientific technical community within India is, can we create sophisticated systems? For example, I make a challenge. I have not made it, but I make a challenge. Can we, for example, have something like a CCTV camera, which has very high resolution for temperature, so that if you put in a place, you can pinpoint which cluster of human beings having higher temperature than normal, or something like this. This is doable, but you need also high quality electronics, high quality detectors, and this type of things will help a great deal into this thing. This I am giving one example. But the problem today is when you have to deal with something like 80,000, 90,000 people all over the country which are affected, they need a lot of infrastructure. That is why initially it took some time, but now the infrastructure is there. Can scientists and technologists help at least reducing the cost, if not improving the quality of the facilities? For example, many medical people whom we salute for their untiring efforts, in spite of being exposed to this deadly virus, they still went on doing their duty with great devotion, and many of them caught the virus. So can we ourselves help in this way? Can we think we can examine many of the fabrics we prepare, many of the materials we prepare, whether we put seeds or beds or whatever. I'm not able to give you all the details. All of you can gather that easily. But question is, can we add electronic detectors into it? Can we add solid state systems which can help improve the situation. So these are some of the challenges which you cannot have. Now coming with this is also the challenge is not merely this. The challenge is that today the world is transforming itself in a major way. We have a tendency, somehow being an Indian, I can share this, it's a self-criticism. Our problem is when we have a subject, if we understand it, we feel the calm ho gaya. We feel we are very satisfied, bas ho gaya. If we only understand, if suppose I say about this virus, if I study the structure, I think this is done. No, it has to be implemented, it has to be executed. That is where our main challenge is. That is where our real challenge is, that how we can put our knowledge into real thing. I want to give an example. Professor Birpal Singh will allow me a little repetition. Last time I gave this example, but this is such a strong example, I can't help repeating it. See, I've connected with many global institutions. There is a very good organization called World Science Forum. This is a very prestigious forum. Every 2 years, they have a meeting. And I have been part of their steering committee, a member of their steering committee. So often I have to go there. So last time, few months ago, the meeting was held in Budapest in Hungary. Is the originator of this. Now every 2 years they have in Hungary and outside and so on. Now here the best talk came from a lady who was IBM. Once most people may not know, while working at NPL, what I developed, I got an invitation from IBM Watson Center. Somebody came, collected biodata and sent me over. And I was called a IBM fellow. And recently in this meeting, I'm not talking of myself, a young lady, 35 years roughly, from Japan, she was introduced as a IBM fellow. And she gave a presentation. And initially it looked like any other very good presentation, outstanding presentation. But she said, I want to tell you how I arrived at this place, even at this podium, without help of anybody. It turned out that she was totally blind. She could not see anything. She had nobody to escort her from her home to the airport. Now she showed what is the artificial intelligence. She had only her mobile phone. And in this mobile phone, when she came out of her home, one can say home, you can even blind people can easily manage. But when she came at home and at the edge of the road, she has to cross, her mobile told her, wait for 1 minute, wait for 2 minutes. She crossed the road. Doing this, she went to the airport. She checked by herself. Nobody supported her. She checked in, gave her luggage for baggage for taking into the plane, and through security, immigration. And when she came there, we never realized, when she sat on this stage for delivering the lecture, nobody realized. In between, she showed some examples. For example, she said, I felt hungry. Then I looked at this mobile, asked him, where are the possible stalls where I can go and get some food. And then she located a stall and she said chips, and she selected an image of potato chips and she would eat it. Now, what I am saying is, this is a real life situation. The artificial intelligence, I find many engineering colleges, I'm also connected with, sometimes go to this K.R. Mangalam University. They have also a course on artificial intelligence. But I asked, can you now show a computer where your algorithms can do this action of artificial intelligence? We have many very active groups in India. Many good people are there. but can we proliferate it to such a level we can use it? And this has to be at a very deeper level, so that particularly in industry, you can do complicated operations, manufacturing with high quality, leading to high quality products, which can compete internationally.
May I request you to conclude in 5 minutes?
I will. I have not much more. I will can anytime I am ready. So now on the horizon, there are this not only artificial intelligence and machine language, there is also the question of quantum computers. Government has already started a scheme on this. One thing I thought I will mention, there is you people may know or maybe beneficiary, there is a DST as a program to support universities in research and development called PERS. So this PERS, I happen to be chair for the program monitoring committee. And again, they have asked me now, next week, we have a meeting to see what new features should we put into PERS. Because the universities must ensure that their level of research goes up. Our problem is that I chaired a meeting to review the PERS performance, 32 universities about 2 months ago. The problem is most of the universities could not utilize entire funds, including JNU, DU, and the funds which were returned were in tens of crores, not 1 or 2 lakhs. So this one thing I would like that universities should make effort that their utilization of support is adequate. If they utilize properly, they can even attract more funding and can be given more support. And finally, I would say, if possible, this every university does project-based learning. Please strengthen the project-based learning as much as you can. I want to show you only 2 slides in the end. There is nothing to talk about it. This is from one of our very famous Upanishad. I hope you can see all. Vijnanam Anandam Brahm. The pleasure you get out of science is God itself. This is what I thought. Oh, ये तो दूसरा बदल गया. Sorry. नहीं, मैं दिखाता हूँ. The basic thing I want to show is that the emphasis on Vigyan, science, is right from the very beginning. In the Upanishad, they say Vijnanam Anandam Brahm. This is the very beautiful definition of Brahm. So thank you very much for your attention.
Thank you very much for so informative and technical come informative lecture. Thank you very much, sir. Now I request, so we are fortunate enough to have Professor S.T. Khare, founder head of our physics department and eminent theoretical physicist. I request Professor Khare for his Ashirvachan. Professor Khare.
Hello. A very good morning to the Honorable Vice Chancellor, Professor N. Ketaneja, to the chief guest, whom we have just heard, Dr. Krishna Lal, and my very old friend, Professor P.K. Gupta, and to all the delegates and ladies and gentlemen. Both Dr. Lal and Gupta are brilliant products of the Meerut College, most famous college of the Western UP, and now more than 100 years old. On this occasion, I cannot fail to remember Dr. R.K. Singh, the founder Vice Chancellor of the Meerut University. He did not want to have any competition with the colleges. Hence, he started MPhil teaching in the university. He was also against the departments. He created divisions of the physics, physical sciences, and biological sciences. For him, merit of the faculty was the only criteria. He offered me full professorship in the division of physical sciences. When I was only 34 years old, due to my young look, I was looking younger than my age. It created many funny situations. Of course, this is not the occasion to describe any one of them. On my arrival at the Meerut, the first faculty member I met was Professor P.K. Gupta. Since then, we are good friends. At present, the country is under lockdown condition, which Dr. Lal has just described, due to coronavirus. But this virus cannot defeat our spirit. All our academic activities are in full swing. The present conference is an example. As the founder head of the physics department, I have been asked to the present head by Professor Will Paul to bless the conference. With great pleasure, I wish a great success to the conference. Thank all of you.
Inspiring lecture. Thank you very much, sir, for your highly inspiring and for your guidance to the department. Thank you very much, sir. Now I invite Professor Vimala Y to bless us to give her presidential lecture, presidential address. Professor Vimala Y, our Honorable Pro-Vice Chancellor, Professor in the Department of Botany. She is a renowned academician.
Thank you very much, Dr. Malik. I hope I'm audible.
Yeah, yes, yeah. Visible and audible.
Thank you very much for inviting me here at this interdisciplinary platform of science and research. I'm really very happy that Chaudhary Charan Singh University made it. The Department of Physics and other science departments have collaborated to offer to the world a common platform for science and a way to interdisciplinary research. Even during this COVID time, when all the other activities are going on in a very slow mode, this is a very great achievement, and I would like to congratulate Professor Birpal Singh and Professor Anil Malik and their team for this effort. At the outset, I would like to welcome and thank Professor Krishan Lal, who has given a very illuminating talk on interdisciplinary science. mentioning about physics and life science together on one platform. In fact, this international platform has put together the luminaries from all corners, and I'm really delighted to see them all. Professor S.P. Khare, the founder head of this department, and shortly we will be listening to Professor P.K. Gupta also, as has been mentioned in the program. Such emeritus scientists, when they appear on one stage, and I can see that the number of participants has gone up to 300, and now it has again reduced to 281. So people are coming and going out. However, I believe that they are all trying to listen to the statements of these luminaries, the scientists who will enlighten us all in every aspect of science. Science as a whole, not physical, not chemical, not biological, not mathematical alone. It's a good occasion to see Professor Mridul Gupta, Dean, Faculty of Science. Then Professor Ramesh Chandra, an old alumni of our university and a professor at IIT Roorkee. I could notice some of them who I recognized from earlier times also. And unfortunately, Professor Narendra Kumar Daneja, our Vice Chancellor, could not join here because of some mishappening, which probably he may join again later. But on his behalf, I am talking to you all, and I know how much does he want that such academic activities should go on in this university. So it is because of his inspiration that even physics people have done this great job. Well, since this is COVID time, and each one of us is thinking about what is happening currently, what is the current state of knowledge, I would like to add something to the talk given by Professor Krishan Lal, that life science people are also not sitting idle. They have also done a little bit of their contribution. And I was listening to a talk to the deliberations by WHO, Director General, Executive Director, and Maria, the lady over there. All three of them were talking about the current state, and some 15,000 and more genomes have been sequenced already for coronavirus. There are more than 53 mutations. In India itself, more than 17 have been recorded. So under this status, we know that we have to live with the viruses because they are also one of the organisms of this earth. However, we have to live protected and safe so that our race and their race both survive together. In fact, we have given way to coronavirus to enter into human periphery as well, which actually it belonged to bats. But this is how the evolution takes place, because survival of the fittest is always there. So they try to survive in their own way. Humans cannot mutate so fast the way viruses or bacteria can mutate. So with the current status of knowledge, what we have today, I am sure that this forum, international forum, and shortly we will be hearing Professor P.K. Gupta also, I am sure he will also throw a good amount of light on the latest happenings and the current state of knowledge of coronavirus. However, I would also like to add one more thing, because I am a botanist, that we, like Professor Krishan Lal was talking about Upanishads, I would also like to say that Ayurveda also has mention of several such medicinal plants. The natural products have proved to be medicinal, though they are secondary metabolites for the plants, defense compounds for the plants, they have proved to be of great drug value for the human beings. And I was reading a recent paper by Prasher and co-workers in one of the Elsevier journals in 2020, April 2020 it has appeared, which also states that how lungs are being affected in 4 ways, and how our natural products can help in curbing the diseases. For example, in that paper, they have shown how from flavonoids, there are glycosides, terpenoids, and alkaloids, we can take care of, we can suppress, we can attenuate, we can downregulate, or we can mutate or mitigate, sorry, not mutate, mitigate the diseases like asthma, lung cancer, fibrosis, or COPD. So if all that is going on, then we are sure that physics, chemistry, mathematics, statistics, biology, they should join hands together in overcoming the problems for humankind. So I would not speak more because there are luminaries, there are galaxy of scientists who are going to speak about interdisciplinary research, the prospects, what we can fetch from them. So I will rather say thank you all for being here, for enlightening us and joining us with one Upanishada sentence again, shloka. Saha navavatu, saha nau bhunaktu, saha viryam karavavahe, tejas vinavadhitamastu, ma vidvishavahe. So let us all join hands for the welfare of human beings. Thank you.
Thank you very much, ma'am, for enlightening us, for giving so beautiful presidential address, and for blessing us. Thank you very much, ma'am. Now I request Dr. Yogendra Gautam to give the vote of thanks. Dr. Gautam.
Good morning to all of you. On the behalf of organizing committee, it's a great privilege to propose hearty vote of thanks to our chief guest, Professor Kishanlal sir, for gracing today's webinar and delivering the inaugural address. Your presence has immensely enhanced the potential of the webinar. Thank you for very interesting and thought-provoking address. We are deeply grateful to our Vice Chancellor sir, Professor N.K. Taneja, for constant motivation, encouragement, and support that definitely inspire us. I'm grateful to our Pro Vice Chancellor, Madam, Professor Y. Vimala, for presiding over this function and for an enlightening address. The address was unique as always because of the novelty of ideas as well as style. Ma'am, your guidance to all our activities ensure that we are always do the right things in right way. I must express my deep gratitude to Professor S.P. Khare, founder, head of physics department, for having graced this occasion and blessed us with her Ashirvachna. My heartfelt thanks to Dean of Faculty of Science, Professor M.K. Gupta sir, and head of various departments, faculty of university and colleges for their valuable guidance in all our effort. I thanks all the distinguished invitees present here, accepting our invitation. I'm also thankful to members of the media for evidence interest in covering the event and all good hearts who worked hard behind the screen. Once again, I thank you all for your kind attention. Now our inaugural session is over, and let us move to the next session, the first technical session. And for that, I invite Professor Anil Kumar Malik to start the session. Thank you so much.
Thank you, Dr. Gautam. I request Professor Birpal Singh to introduce the first invited speaker, Professor.
Thank you, Professor Malik. I feel honor and privilege to invite great personality, Professor P.K. Gupta, who will deliver very first invited lecture of this conference. Professor P.K. Gupta earned his PhD in 1967 from University of Manitoba, Canada. He has supervised more than 80 PhD students and published more than 440 research papers in national and international repute. He visited many countries like Canada, USA, Mexico, UK, France, Germany, Switzerland, Syria, many more, Australia, Japan, for presenting his work and for PDF kind of research work. Professor Gupta has also written more than 24 university level textbooks. It's a great contribution of Professor Gupta to give that kind of textbooks and reference books to our students across the globe, which are widely read, and also edited a couple of volumes associated with Macmillan, Elsevier, and Springer that are used as reference material in the field of genetics, cytogenetics, and biotechnology. It's a fellow, he is a fellow of the National Academies in the area of science and agriculture in India. He is FNA, it's a matter of proud for us. He is FNASC, he is FASC, he is FNAAS, and also earned various academic awards, including the prestigious Birbal Sahani Gold Medal of the Indian Botanical Society and the ABLE Award for Excellence in Agriculture Research in 2013 for his significant contribution in the area of marker-assisted selection for crop improvement. By this very small introduction of Professor Gupta, I humbly request Professor Gupta to deliver his invited talk.
Thank you, Dr. Birpal Singh.
Thank you very much, sir.
How do I show there?
Yeah, you can share your slides, sir. Go to
Share slides right away?
Yeah, you not right away. You just share your screen.
Okay.
Can you share?
Can you see the slide?
No. You just go to the share screen and then click on the desktop. If you have your PPT on desktop, then you can open.
Host disabled.
Oh, disabled. Okay, sir. Let me check. So you are already host. I think you can share.
And share?
Yeah, you can share. Yeah. Now you can share, I think.
Can you see?
No,
Okay.
you just go to the share slides.
Share screen first.
Okay. Let me just see.
Yes, sir. Share screen.
Host disabled attendance screen. Host disabled, it says.
Yeah, you can share now. I think there was some issue. You just try again.
Yes, now it's there. Stop sharing. You are screen sharing. Okay. Just a minute.
Yes, sir. Go to the slideshow mode.
See waiting room. Okay.
Should I share your? Yeah, can I share your slides?
Okay. You have my presentation.
Yeah, sir. Sir, I don't think I have your PPTs. Let me check. I don't have your PPT. I think I missed it, or I can just help you out. You just go to the share screen.
Okay,
Have you done it?
just a minute.
You will see a desktop picture.
I have gone to the share screen.
You just see the desktop picture on your screen.
Desktop, yes.
Yeah, you just attack. Okay. Now you will see your desktop, whole desktop. Please wait for some time. Yes. Now you can just.
Can you see?
Yeah, I can see, but this is, I think, not in full. You can go to the slideshow mode. Yeah, right now you can go to the slideshow mode.
Slideshow?
Yes. You can.
Can you?
Yeah, you can just go to the show mode, slideshow mode, or presentation mode.
Press F5.
Stop share. You are
not screen share, sir. It is already visible. You go.
No, but I'm already sharing.
Yeah, it is already shared, but it is not full screen. In fact, you can go to the lowest bar.
No, it is full screen. It is full screen. It is full screen now.
Yeah, right now it is okay.
Yeah, it is okay.
Can I start now?
Yes, it is okay. You can continue with it.
At the outset, I like to thank the organizers for giving me this opportunity, and I'm very pleased to see Professor Khare, who has always been a source of inspiration for me. And I am also pleased to see Dr. Kishan Lal. I had opportunities of meeting him at INSA meetings, and both of us are alumni of Meerut College long time ago. Perhaps I was a little senior to him because I did my master's degree in 1958. I do not know when did he complete his master's degree there. But nevertheless, the topic of this particular conference, which is interdisciplinary in nature, I will not talk much about COVID-19 or the coronavirus, but the discipline which I profess is genetics, genomics, and cell and molecular biology. This discipline is purely interdisciplinary in nature, and this subject is taught in large number of subjects in life sciences and agriculture and also biotechnology. Therefore, the subject of my study is purely interdisciplinary in nature, and with the help of some examples and the history of this subject, I will explain to you what interdisciplinary nature really means, because all advances in the field of genetics have been made through interdisciplinary research in chemistry and physics. They have contributed to the development of genetics in a large way. And the first, why can't I move? Next slide. Oh. No, not working. Well, what I wanted to show is that the origin of the subject of biology took place through an interdisciplinary research in 1665, 355 years ago, when a physicist, Robert Hooke, who also proposed Hooke's law for the students of physics, he was the person who developed a primitive microscope in 1665 and observed a piece of cork where he could observe the cells, and therefore he was the first person who coined the word cell for the structures which have been studied. There is problem with movement of the slides. Yeah. But nevertheless, you see, after this initial discovery of cell by Robert Hooke, there were extensive development in the area of cell structure. Cell structure has been studied through a large number of different types of microscopes. Optical microscopes have been greatly improved, and large number of different types of electron microscopes also developed. And as a result of this, 2 Nobel Prizes, one in 2014 for for the development of fluorescence optical microscope, and one in 2017 for the development of cryo-electron microscope were awarded, suggesting that the developments in the field of physics and chemistry were responsible for major developments in the science of genetics. This cryo-electron microscopy, which was developed maybe about 10-20 years ago, was also responsible for giving us the structure of coronavirus. You can see the picture of coronavirus, which is depicted here and is shown with the help of cryo-electron microscope. And yesterday or day before, I was reading that so much literature is being published on coronavirus. 4,000 papers on coronavirus have been published only during the last 1 week. And 25,000 papers on coronavirus have been published since January this year, during the last 4-5 months. 25,000 papers on coronavirus have been published. Once I thought of writing an article on coronavirus, but I thought so much is being published, you can't even read all that. I will have some examples of Nobel Prizes showing you the progress of genetics through interdisciplinary research. For example, in the year 1927, for the first time, Dr. H.J. Muller demonstrated for the first time that X-rays could be used for development of induced mutations. You see, induced mutations are the basis of studying genetics, because for many traits we don't have variability available in nature. Therefore, you have to induce mutations, create variability for the study of genetics of a large number of different traits. Therefore, it was a boon when in 1927, Dr. Muller gave a technique where X-rays could be used for inducing mutations. Similarly, chemicals could also be used for inducing mutations, and this was demonstrated for the first time by the lady C. Auerbach at the University of Edinburgh, and she was awarded the BSc degree of University of Edinburgh in 1947 for this one. Another Nobel Prize winning discovery, although it was not awarded a Nobel Prize, was the discovery that DNA is the genetic material. In 1946, these three scientists, Avery, MacLeod, McCarthy, for the first time demonstrated, because there was a controversy whether protein is the genetic material or DNA is the genetic material, because the chromosomes which carry the gene, they have two important chemical components, protein and DNA. And these three scientists for the first time demonstrated that DNA is the genetic material. And therefore, in the following year, major work concentrated on the study of DNA. In 1953, Watson and Crick in England, for the first time, worked out the structure of the DNA double helix, and they utilized the X-ray diffraction pictures, which were developed by Rosalind Franklin, a lady who died very early and therefore could not share the Nobel Prize. And this, for the first time, was utilized, X-ray diffraction pictures, to demonstrate that DNA is a double helix. And with the help of this DNA structure, later on, starting from 1953 onwards, there was a very, very productive period of research which has been witnessed for the development. You see, during the last 60 years, I have witnessed the growth of genetics at an exponential rate. You can see in this particular picture the different components of protein synthesis machinery, as DNA is utilized and gives rise to an RNA, and then with the help of transfer RNA and ribosome, the protein synthesis takes place within the cell. And the structure of this machinery, protein synthesis machinery, the ribosome, was worked out by Dr. Roger Wheatcroft, who was awarded Chemistry Nobel Prize in 2006. So you can see that large number of Nobel Prizes have been awarded, although there is no Nobel Prize in biology, but the Nobel Prize of Physics, Chemistry, and Medicine have been awarded in areas which were very instrumental in the growth of genetics and molecular biology. Then, after the discovery of double helix model in 1953, there was a period of very productive research during 1960s, where genetic code, I mean, how DNA gives rise to the protein structure. There are two languages, the nucleotide sequences in DNA and the amino acid sequences in the protein. And we did not know at the time how this language of nucleotide is translated into protein, and therefore Dr. Khurana and 2 or 3 other scientists, they were instrumental in working out the genetic code during the period 1960 and 65. And there are 64 codons, which you can see in this table, which code for 20 different essential amino acids. Dr. Hargobind Khurana was also responsible for synthesis of the first eukaryotic gene, which was a yeast transfer RNA gene, and he was awarded Nobel Prize in 1968, along with 2 other scientists. Then another very important name is the name of Frederick Sanger, who earned a Nobel Prize twice in chemistry in 1958 and then in 1980. First for the structure of insulin protein, which is responsible for diabetes, and the other is in DNA sequence of a virus, 5X174, which was awarded in 1980. And you can see that this man, Frederick Sanger, developed the techniques for DNA sequencing and amino acid sequencing, which was responsible for increased growth in the area of molecular biology and genetics. Another very important name, an Indian-born scientist, Venki Ramakrishnan, who was brought up in India and did his master's degree in India, and later on did his PhD in physics from Ohio University. And during his physics PhD degree, he found biology to be the very exciting subject, and therefore he decided to do a second PhD in biology in California, which he started and continued for 2 years, but later on discontinued because he was offered a postdoctoral position to work in biology, the structure of ribosome at Yale University. And from there onwards, he then moved to England, where he continued till today, and he has been the chairman of the Royal Society, and he was awarded Nobel Prize, as most of you might know, in 2009 for the structure of ribosome. After this, one of the important area of research which has grown exponentially during the last about 25 years is the area of next generation sequencing, next generation genomics and post-genomics era. The first generation sequencing was developed by Frederick Sanger. I have already shown his work to you. And then later on, during the year 2005 onwards, there was a competition for developing techniques for DNA sequencing, which would be cheaper and would be high throughput sequencing. And therefore, second generation sequencing and third generation sequencing was developed during the period of last 15 years, starting in 2015, as a result of which now human genome sequencing, which took about $3 billion and 15 years of research by 50 different labs, now it can be done at a cost of only about $100. And any individual can go. There are facilities available. There are vendors available in USA where you can just go and give a drop of your blood and get your genome sequenced and find out what kind of problems you might have during the time of your life. Another area which has grown during the last about 10 years is single cell genomics. You can now study that sequences, RNA sequences within different cells of the same tissue to find out the heterogeneity in the expression of genes in the different cells of the same tissue, which explains how the tissue really functions. Other areas which have grown from this particular sequencing technology development are genome versus transcriptome, exome, epigenome, metabolome, microbolome, and 3D structure. This slide shows the whole genome sequencing techniques. There are 2 techniques available for whole genome sequencing: clone by clone sequencing, which was the first technique developed for human genome sequencing, in which we physically map the different DNA pieces onto the chromosomes and then sequence utilizing the physical maps. But later on, this technique was taken over by shotgun sequencing, which is shown in this picture, which is a very fast technique, although you have to do more sequencing. But in majority of cases now, the shotgun sequences is utilized for sequencing whole genomes. And hundreds and thousands of species have been completely sequenced during the last about 15 years. And now we sequence a large, for example, in human beings, thousands of human beings' genomes have been sequenced. For example, in England, in coronavirus period, they are trying to sequence the genomes of human beings who have recovered from coronavirus or not recovered from coronavirus to find out whether there is a difference in the genome sequences of individuals who are responding differently to coronavirus. And that is the basis of this personal genome sequencing era, where you try to find out the response of an individual. For example, you also have to find out the genome sequences different with respect to response to different drugs. The same drug for the same disease cannot be prescribed to everybody, because the same drug, the response of different individuals to the same drug will be different. This is the first genome which was sequenced, Haemophilus influenzae, a microbe, which was sequenced in 1994, which laid the foundation of an era of genomics research, which in 25 years flourished exponentially, and large number of genomes have been sequenced. And within the species also, we have thousands of genomes are now being sequenced to see the variation in the genome and to find out what this variation really means. Yes, another picture. You see, in the, I want to emphasize that these developments in the field of genetics and genomics have great role in two major areas for human beings. One is the food security, and the other is human health care. This I've been talking about, and very briefly I would like to explain it. In this particular slide, you see the fields where the crops are being grown. These crops are being grown, and during the last 50 years, we have been recording data manually. Our students go to the field and record data, and then try to apply genetics to find out the genetics of these traits. But now this lacks precision. When students go, sometimes they take help of the laborers also and record data, and this data is not very precise. And therefore, it leads to wrong conclusions. And therefore now, a new science has developed, which is called phenomics, in which we record data with the help of cameras using drones and aeroplanes. And this data is very precise, and using artificial intelligence and machine learning, this data is then utilized for trying to find out the genes which are responsible for different traits. Similarly, this technique of genomics is being utilized for personal genomics. This is an important area which is being commercially exploited in different areas of the world. There are a large number of vendors in USA who are providing this facility. Just after the birth of a child, you can go to a vendor and get the genome sequenced, and you can find out what kind of problems this child might be having throughout his life, so that you can take precautions in the life to avoid the problems which are due to environmental activities and due to other extraneous reasons which are not really genomic in nature. Technology development now allows it just for $100. I told you that there are $3 billion were spent on human genome sequence, which was published in 2003. But after that, the technology development, because of interdisciplinary research, allowed the price to go down from $3 billion to $100, and $3 billion is spent on during 15 years by 50 different labs in the world. And now it can be done within a few hours at a cost of only $100. So that you have such a technology available only because of interdisciplinary research, which can be utilized in order to solve many, many human health problems. In summary, there are two major, as I told you, genetics to genomics for food security and human health care is an exciting journey of interdisciplinary research, which is the fastest growing subject in science. You see, the genetics had its birth only in 1900 with the rediscovery of Mendel's laws, but during the last 120 years, I have witnessed that this is the fastest growing subject involving interdisciplinary research, and not many scientists in our country are really undertaking interdisciplinary research in the true sense, and therefore we are not able to contribute to the same extent as many scientists in foreign countries are doing. But in our own lab, we are doing some interdisciplinary research involving collaboration with a number of scientists, not only in India, but also in the United States. And therefore, to some extent, we can say that interdisciplinary research is being conducted at CCS University, Meerut. And biotechnology, bioinformatics are two other disciplines which are also interdisciplinary in nature, but both of them make use of the genetics and genomic resources. With these words, I thank you very much for your patient hearing.
Thanks, Professor P.K. Gupta, for very nice presentation. And I think that very first presentation really based on interdisciplinary science. which you discuss in your lecture, starting from sequencing, genome sequencing, structure of DNA, and in addition to that, you mention very latest kind of electron microscope, cryo microscope,
Yes.
XRD and all. We are thankful to be with us and delivering so wonderful lecture and bless us. Being the senior most professor of this university, I really thanks to you for your blessings and all, and to be with us in this interdisciplinary theme based conference, e-conference. Thank you, sir. Thank you very much.
Yeah, thank you. Thank you.
Now, our next speaker is Professor. Next speaker is Professor Dinu. Professor, I welcome Professor Dinu Javransky. Professor Dinu Javransky is working in University of Scranche, Glasgow, Scotland, UK. Professor Dino was born in Helsinki and grown up in South Africa, sorry, and arrived in the UK in 1976 to complete his BSc honors and for his PhD studies in physics at the University of Manchester after being inspired by philosophy of science at the University of Cape Town. He comes from a family of artists. This inspired an interest in mediums of arts as a language of science to Professor Dino. Professor Dino is a well-known plasma physicist. He founded the Scottish Centre for the Application of Plasma-Based Accelerators, which is known as SCAPA, where he uses high-power lasers and plasma as compact radiation sources for applications of value to society. His contributions to science include pioneering advances in laser plasma accelerators and compact particle beam based radiation sources. It's a matter of pride that he has published more than 139 research papers in peer-reviewed journals of very high international repute. His research citation is again very high. He has more than 10,000 citations of his research. With these words, I welcome you, Professor Dinu, and I humbly request you to deliver your invited talk in this conference. Professor Dinu.
Thank you very much, Dr. Malik, Professor Malik, and also Dr. Verma, for inviting me to this prestigious meeting across continents. It's my pleasure to give you this talk. And I think what I'll do is I'll try and first share screen so you can see what I'm going to talk about. Let's see, how do I share screen? Screen, yeah. Okay, share. Give this thing. So today I'm going to talk about how one can use plasma. Plasma is the fourth state of matter, which forms more than 99% of the visible universe and has some quite interesting properties because it's a dielectric medium, so it can influence the propagation of light. And also by separating charge in plasma, one can produce very large electric fields, and you can use plasma as an accelerator. So what I'm going to do is tell you a little bit about this, about the work we've been doing, and showing how this plasma can be used as a basis for new technologies that can potentially replace or at least work besides, for example, large light sources, some of the largest instruments in the world, synchrotron sources, and free electron lasers. And so I come from University of Strathclyde in Scotland, in Glasgow, a country which has several quite important, has been the home to several very important physicists like James Clerk Maxwell. Can you hear me, Professor Malik? Yeah, good. And Lord Kelvin, and also several other very important scientists. So what I'm going to do is tell you a little bit about how laser plasma interactions, how to produce a plasma, firstly, how to separate the charge, and then to use, to accelerate charge and use these charge beams to produce electromagnetic radiation of a very large spectral range. I'll tell you a little bit about that. I'll tell you about the progress and plans for the future, and how to make these devices extremely compact. And you'll get some idea of the scale of these. And finally, I'm going to talk about one of the sort of applications of lasers is also how one can use plasma as a dielectric medium for amplifying light. So in other words, to use it as a laser type of amplifier. So there are about 35,000 accelerators around the world. They're used extensively in many areas, in manufacture and in radiotherapy, for example, and as a basis of light sources. But generally, they are produced by, they are constructed out of microwave cavities, which can only withstand a field gradient up to 100 million volts per meter. And therefore, they are quite large devices. So for example, the CERN device, the LHC in CERN is 27 kilometers in circumference. And that's really partly because the accelerating gradient is relatively small. It's about 27 megavolts per meter. But if you have plasma, if you take plasma, which is, as I said, the fourth state of matter, and you can separate charge, you can produce fields up to 1 teravolt per meter, or of that order. So in principle, if you could harness these forces in plasma, you could put CERN in a 7-meter room. But the trick is how to harness the plasma. So I'm not going to tell you about how to replace CERN, but rather how to make light sources. So light sources about the size of 5 football pitches, or free synchrotron sources, or free electron lasers, which are about 3 or 4 kilometers long. And these devices cost hundreds of millions of pounds. And free electron lasers cost billions, several billion pounds to construct, and they are huge devices. So if one can replace some components of these devices by plasma, using a laser, for example, to drive the plasma, because you can use a laser, very intense laser pulses, to apply pressure to plasma, to fully ionize gas to make plasma, apply the pressure to plasma, and separate the charge. And because you can do this using light, you can separate the charge at the speed of light. In other words, you can have a traveling wave structure which has a very large field. So if you can see my figure here. On the bottom right-hand side, you can see what happens when you focus an intense laser pulse into plasma. You separate the charge, because plasma wants to remain neutral. The charge will always try and return. You separate the electrons from the protons. And the electrons always want to return to the protons or to ions if you separate heavier particles, heavier atoms. And they oscillate locally at the plasma frequency. So they have a very regular oscillation, and they leave a wake behind the laser pulse, very similar to the wake behind a boat. And the scale length of this is quite incredible, because if you think about a conventional accelerator, there are tens of centimeters in diameter, the accelerating structures. In plasma, you can make these tens of microns. So you can make them about 1,000 times smaller. And also you can make the fields maybe even 10,000 times larger. So that means you can make these devices very compact. So for example, you could make, and this is the state of the art at the moment, you can make an 8 to 10 giga-electron volt accelerator that's only a few centimeters long, which would be possibly 100 meters or more long. So you can make them very, very compact. And this means that you can think about using them as the main component of accelerator technology, a very compact accelerator technology, so that you can make these accelerators more widely available, more accessible, and therefore you can stimulate the growth of science and application in technology and in therapy, for example. So it's very easy to create plasma using a laser. All you need to do is have a high intensity enough laser and focus it into gas. Normally you'd use hydrogen or helium, and that would fully ionize the gas. So you take off all the electrons from the ions, and you make a gas out of the heavier ions and the lighter electrons, which remain quasi-neutral. And if you use a very intense laser beam, so you use a few joules of laser pulse over a duration of several tens of femtoseconds, you can produce powers, peak powers, of the order of tens to hundreds of terawatts, or even a petawatt. And that's much higher. This power is much higher than the world's consumption of power, but of course only for a short time. And you can, if you focus these lasers into a small spot, you can make the electrons that you produce in making the plasma, you can drive these up to the speed of light. So you make the plasma relativistic. So you start changing the mass of the electrons that are being driven by the laser pulse. And this means that you can change the optical properties of the plasma. So that when a laser propagates in this plasma at these very high intensities, these relativistic effects can cause phenomena like self-focusing. So rather than the laser pulse diverging and diffracting into space, it becomes self-focused, and it can guide for a very, very long length relative to the Rayleigh length that it would normally diverge at. So you can make these very small, very compact devices. You can make these very fine channels. These are 10 microns or a few tens of microns in diameter, of several centimeters in length. So from millimeters to centimeters in length. And you can do this using a laser. You can also use a charged particle to do that. But what I'm going to be talking about is just using the laser to apply the force to the plasma to separate the charge. So if you focus this light beam into the plasma, you can expel all the electrons from a region. The ions are heavy, so they don't move on the time scale at which the electrons separate from the ions. And the huge forces that the ions left behind apply to the electrons will pull the electrons back, and they will oscillate at this plasma frequency, which is a very high frequency. You're talking about tens, even to hundreds of terahertz.
Hello?
So you can produce a structure. So what you see on the figure here is an evacuated region where you only have ions surrounded by a sheath of electrons. Now this bubble is traveling along at the speed of light, almost at the speed of light. Of course, nothing will travel faster, no information will travel faster than the speed of light. So this bubble will travel along just slower than the speed of light because the laser pulse interacts with the plasma. So it causes the laser pulse to travel slightly less than the speed of light. So you have the structure traveling along what we call a traveling structure. And it's very, very well defined. And the fields inside the structure are incredibly high. So you're talking about, for the sort of work we do, 100 gigavolts per meter. And you can even, with high enough density, you can even go up to a teravolt per meter. And so the question is, how can you use this as an accelerator? And in 1979, John Dawson and Toshi Tajima proposed this concept. And in the last 50 years, people have been trying to demonstrate this. And like any new technology, it takes time to develop the technology. And it was only in 2004 where this was first demonstrated. So this is already 16 years ago. And the demonstration was carried out by, the first successful demonstration was carried out by 3 groups. One group led by a project that I was the head of, called Alpha X in the UK, another one in Berkeley, and at the Lawrence Berkeley National Lab, and then in France at the LOA laboratory, Laboratoire Optique Applique. And so the structure you produce looks something like this, with this wake behind it, traveling behind, just oscillating regularly at the plasma frequency, just like the wake behind a boat. And it travels, the laser pulse travels along with the group velocity of the laser pulse, which is slightly less than the speed of light. And it leaves behind it regions where there are evacuated electrons and regions where the electrons are built up. And these all oscillate locally at the plasma frequency. So one analogy to this, of this type of structure, is a surfer surfing on a wave. So if you imagine that the bubble is effectively like a wave, and any particles you put in the bubble will then see the forces, electrostatic forces of the bubble, and then will accelerate forward. Now the bubble will travel at a velocity slightly less than the particles, because light particles like electrons will very quickly accelerate to very close to the speed of light. So they will travel along at a larger velocity than the bubble. Even though they both travel along the speed of light, the relative differences in the velocity means that the electrons, or electrons that are inside the bubble, will move forward in the bubble, just like a surfer will surf down a wave. So the surfer surfs down a wave and acquires momentum from the wave. So that's the basis of this type of accelerator. And turns out that you don't even need an external electron beam for these accelerators. The electrons can come from the plasma itself. The forces are so large that the electrons are sucked into the back of the bubble in quite a controlled way, and they can accelerate. And because the bubble travels along at a slightly slower velocity than the particles, the electrons will eventually catch up with the middle of the bubble, and they will outrun the accelerating part of the bubble. So the field will go from positive to negative in terms of acceleration. So that means that it sets a finite length for these accelerators. And that sets some of the basic scaling properties of these accelerators. So it means that if you want to build a low energy accelerator, you go to high density plasma and to a larger field where the laser pulse travels slower in the plasma than in a less dense plasma where the laser pulse travels faster. Now, when the laser pulse travels faster, it means that the electrons take longer to catch up with the middle of the bubble. So you can accelerate to higher energies. Okay, so that means that if you want to accelerate, for example, to 10 GeV, you need a density of around 10 to the 17 electrons per cubic centimeter. If you want to accelerate up to, let's say, 10 MeV, you need a density of 10 to the 19, 10 to the 20 of that order. So that's the basis of it. And the sort of lasers you need to use are lasers which we call terawatt lasers, which are relatively compact. They're desktop lasers. They're not like pointers, but they are laboratory size. And the accelerator itself is of the order of millimeters in length for the sort of accelerators I'll be showing you now. And so if you want to study these, you need to build a laboratory, which looks a little bit like a large laboratory, a large accelerator laboratory, but it's much more compact because most of the components in the laboratory are components for transporting the electron beams and maybe producing electromagnetic radiation. So you can see on that figure there, the layout of what we call a beamline for studying this accelerator. And also you can see on the right-hand side an undulator. An undulator is the main component of synchrotron source or a free electron laser, and this is to study how we can use these particle beams produced by these laser-driven accelerators. The smallest part, you're talking about these are about millimeters in size. You see here on the left-hand side. I think there's some people that should turn their microphones off. So you can produce actually relatively good quality beams because the accelerator structures are only 10 or few tens of microns in diameter. It means that the quality of the beams that you produce can be quite good because they fill a small volume. These beams are incredibly small. The volume of only a micron or less cubed. So the current density is very large, and the energy spread of the beams can be very small. Now that's a property that you want. I think some people have got their microphones on.
Lots of disturbance.
So you can produce relatively. Okay, I think everybody should turn off their microphones. Okay, so that means you can produce beams which are actually quite good. Which you can produce beams which are something like the best quality. Because you won't hear me now.
Please unmute your mic.
I know. I just have to. Okay, I think it's unmuted now. Can you hear me?
Yeah.
Okay, very good. Okay, thank you very much. So what this means is that you can produce a good quality beam from these tiny accelerators, and you can think about using them. So these have the qualities of some of the best accelerators in the world, even though they're very small. So what I'm showing there is.
You unmute.
Yes. Yeah. Thank you. Yeah, thank you very much.
Audible now.
Yeah, I see you've unmuted me. That's good. And you can also accelerate the particles to high energy. So what I showed you before was accelerating particles to about 140 MeV, which we've done in our lab, and up to about 1 GeV. And so these are the energies that you need, 1 GeV to 10 GeV to make a compact synchrotron source or a compact free electron laser. And the quality of these beams is actually quite good. Lots of work needs to be done because the real challenge is having a very good laser. So people who work in this area always struggling with the lasers. Okay. And I'm sure that people who work in this area will confirm this. So it is a challenge, but we have to persist, of course. And so the momentum spread of the electrons is important, the longitudinal one, which gives rise to the energy spread of the beam. But the transverse momentum spread is also important because that allows you to transport the beam and to keep the electrons, if you're making a free electron laser, to keep the electrons in phase. So you measure the transverse momentum spread of a particle beam using a property called emittance. It's the analog of the wavelength of light. So it means that the smaller the emittance, the easier you can focus the beam. In other words, like light, if you have a shorter wavelength of light, you can focus to a smaller spot. So you can make a much more intense beam. Okay. So these are measurements that we've done, which show that we've measured emittances that are amongst the best in the world of any accelerator. A very interesting property, which is unlike any other accelerator, is the bunch length, the duration of these charged particles. Now, turns out that the way these electrons inject into the structure allows them to be shut off, the injection to be shut off almost immediately. So you can produce very short pulses, extremely short pulses. you can produce pulses of the order of 1 femtosecond. So 1 femtosecond is 1/3 of a micron in length. So it's incredibly short electron bunches. If you compare it with conventional accelerators have tens to hundreds of femtoseconds for the best accelerators, and for synchrotron sources, you're talking about picoseconds. So you have a type of accelerator which has a unique property, and because the bunches are very short and very condensed in a small volume, the current is very high, and that's what you need for a free electron laser. If you want to make a coherent radiation source, you need a very high current and a very good quality beam. So what I'm showing here is how these beams can be made absolutely unique and potentially possible to use as a light source. And I'll show you the steps that we've taken to investigate that. But that's not the end of the story, because actually you can devise methods of going even to shorter pulses. You can go to pulses which are of the order of attoseconds in length. Okay, you're talking about 10 to the minus 18 seconds is an attosecond. So these are very, very short pulses. So by modulating the density of the plasma on a short scale, one can actually control the injection.
Sir Dino, please, you are requested to conclude within 2 minutes, please.
Yes, I'm concluding in 2 minutes, yeah.
Thank you.
So you can make very short pulses, and you can also produce very high charge pulses. So this shows you a simulation of producing these electrons. So what you'll see now is electrons being injected into the back of the bubble. These are electrons above 1 MeV in energy. And some electrons are not trapped, which are there streaming backwards, because this frame of reference is moving at the speed of light. And these electrons will come out with very high charge. So you can produce unique beams which have a charge which are larger than almost every other accelerator. And the bunches are very short. You can see there on the right-hand side, those are the high energy beams, talking about beams which are hundreds of mega electron volts, less than a femtosecond. These are beams with 300 attoseconds in length. And so you can produce these very high charge beams which don't get trapped, and you can produce very short bunches which do get trapped. Okay, so you can produce even up to about 500 nanocoulombs of charge at relatively low energy that are not trapped, and of the several tens of picoseconds of ones that do get trapped. And these can be used for applications. But the most important application is producing a synchrotron source. So you can take the beams and you can pass them through an undulator, as in a synchrotron source, and it can produce electromagnetic radiation. This is the first demonstration that we did, where we showed this happening in the visible, and we've now extended it into the UV, the XUV range. So it shows that you can use this as a standard accelerator with a conventional undulator. But you can also use the plasma as an undulator to go to very high energies, photon energies. So if you think a synchrotron source, you could produce photons up to tens of keV. Well, with the plasma as an undulator or a wiggler, you can produce photons up to 7 MeV. So we've demonstrated that in the lab, and that is quite extraordinary. This is a wiggler with properties that are just not available anywhere else. You can even think about building these into a free electron laser. And you can then build a very compact free electron laser. You're talking about a free electron laser that's centimeters in length compared to kilometers in length. So this is all work in progress that our group is involved in. And I'm going to just show you this while I finish off, which just shows you where we are in our work. These are plots of the brilliance, the peak brilliance of these sources. And these are synchrotron sources, these solid lines here, and the straight lines above are free electron lasers. And all the points that I've got here, the solid points are where what we've done. This is where we plan to go with an incoherent source, a synchrotron source. So we can make something that's much better than a conventional synchrotron source. And if we get the free electron laser to work, we can make a compact free electron laser, which is equivalent to those billion pound free electron lasers. And so I was going to talk about how to use the plasma as an amplifier. So I'm going to skip that because I've run out of time. And so I'm just going to go right to the end and to thank my colleagues for for helping me over the years and all the collaborators that I've got. So and I'd like to thank you all for inviting me to this conference, teleconference, and
thanks, Professor Dino. Professor Dino, thanks for delivering so wonderful talk on fourth state of matter, that's the plasma, and you nicely explain the application of that kind of fourth state of matter in different fields of technology, especially accelerators, amplifiers, and radiation sources. You come from all the time in from Scotland, UK, and join us. Thank you very much, Professor Dino, for connecting with us.
It's
now
my pleasure. Thank you very much.
Thank you very much. Thank you very much. Now for introducing next speaker, I invite my colleague, Dr. Sanjeev Kumar Sharma. You please give the introduction of next speaker in this webinar. Dr. Sanjeev Kumar Sharma. Dr. Sharma, please unmute yourself.
I'm sorry. Good afternoon to all. And I'm thankful to the organizing committee and convener of this conference, Professor Birpal. And it's a very wonderful initiative of this program. Now, I'm introducing Dr. Anton. It's my great honor to introduce Dr. Anton Radix, who earned his PhD in physics from Lozef Steffen Institutes, University of Ljubljana, Slovenia in 2012. After his PhD completed, he remained the research associate at the Korea Basic Institute in South Korea in 2012 to 2013. Thereafter, Dr. Anton was worked as a Fulbright Fellow at Washington University in St. Louis during 2014 and 15. After 2015, he joined the Lozep Department of Intelligent Systems and Department of Solid-State Physics, Steffen Institute in Ljubljana, as an assistant professor. He has research interest in development of materials for the hydrogen economy, liquid crystals, and their applications in interfacial intelligence in the field of medicine and bomb-based, etc. So, Dr. Anton, please, you are welcome, and give your experience, and we are ready to learn from you. Dr. Anton.
Thank you all. Testing, do you hear me? Can you hear me?
Yeah, you are audible.
Yeah, we can see.
Can you hear me?
Yeah, we can hear.
Okay, good. So let me start. First of all, I would like to thank for this kind of introduction, and I would like to thank the organizers for giving me the opportunity to present some part of our work. So after the first two talks were, I would say, basic science, like hard science, this talk will be about applied science. So as the introduction mentioned, I started as a pure physicist, but now I shifted my work also to artificial intelligence. And this talk will be about application, about some issues that are facing the elderly in the modern society. But before I continue, I would like to introduce where I come from. This is Joseph Steffen Institute in Ljubljana, Slovenia, named after Joseph Steffen, the physicist from 19th century. He was from Slovenia, and he studied black body radiation. So this is the Stefan Boltzmann law. We are about 1,000 researchers at the Institute. We have strong cooperation with the University of Ljubljana, with different research organizations and universities in Slovenia and also worldwide, as well as some companies. We have departments for physics, chemistry, biochemistry, bioinformatics, and environmental sciences. And this is the campus. And this is our group department for intelligent systems. What are some of the issues that the society is facing? So on the right, you can see the demographic pyramid for Slovenia. It's typical for, let's say, for Europe or some Western countries, meaning that there are more people in the working age than there are young people. In some time, this will bring problems because people in the working age will retire, and many of them will require assistance. Some will go to nursing homes, some will need assistance from home. And because there are not enough young people, there will be severe problems with the availability of people to provide care and services. This is why the World Health Organization is promoting policies such as active aging and healthy aging. And this indicates that people should live their life at its fullest, even when they age. So they should have accessibility to different services, and they should also feel useful, and they contribute to society. As there are not enough people to help, we have to turn to information and communication technologies to assist all these tasks. Also, in the time of coronavirus, since we have social isolation, these techniques, as you see, can already help because people simply, not that there are not enough people to help, but people cannot access the elderly because of the distancing. So I will present you some of the ideas how we can use these technologies. First, if we compare a human carer to a virtual carer. Now, I'm not talking about robots, which will help in the household, because these are still, let's say, several years in the future, but I'm just talking about virtual technologies, how they can help it. So what can a human carer do? Well, pretty much everything that a human carer, that you imagine by a human carer. So they can talk to people, they can help with the household tasks, they can check health status, and they can offer emotional support, things like that. However, there are some drawbacks of where the human is not available all the time. It's expensive because you have to provide the salary, and since the human is not there all the time, it cannot adapt easily to changing situations. On the other hand, a virtual system can in principle work 24/7. It can adapt to any changes in the situation, like if there's a medical emergency, and it's low cost when you install it. Of course, before we start using virtual carers, we have to solve a series of problems first. One is the design. Such system have to be designed in a way that the elderly will be comfortable using it, because if a person from the engineering background, so as we were designing some systems, we realized that what is intuitive for us may be less intuitive to, let's say, to our grandparents. Then the important problem is privacy, because these systems are ICT solutions, so they're typically connected to some external services via internet, and therefore they are prone to abuse, spying, or other infringements. So they have to be secure in order to for the users to accept them. They have to be reliable. In case of an emergency, they have to act immediately and properly. It's a benefit if they're interoperable, if they can connect to other devices that the users are having. And one of the main problems we identified is that the elderly are typically reluctant to start using these kind of devices. So, but this will change. For example, our grandparents' generation did not grow up using electronic devices. Our parents are already very familiar with smartphone and similar technologies. And if you look at younger generations, they are already using electronic devices such as smartphones, wearables, games from the very early age. So while they, by the time they grow up, they will be perfectly used to using electronics. what we developed is a concept of intelligent active carer for active aging, which was developed within the framework of a European-funded project in life, which included several partners from various European countries. Such system is modular, and the idea is that it should be adapted gradually. So active users, let's say elderly, which are still living independently, they're healthy, they don't have any problems, they don't need assistance. They may first use such some of the components, for example, a fitness tracker. And later, when they start experiences health problems, they would be able to add modules, which are security modules or health-related modules. So this is a kind of overview of the system. It has a platform that connects to the servers, and it has different modules with different tasks. These modules are coupled to the sensors in the hardware. So it can be either internal sensors of, for example, a smartwatch or a smartphone, or external medical devices such as ECG monitor or blood sugar and blood pressure devices that are used for certain chronic diseases. What is the benefit of using different combinations of devices? So we get enriched data, which gives us a better insight into daily living of the users. And this gives us also improved performance in monitoring and detection of possible complications. So we can recognize the context, we can monitor the parameter trends, especially for deterioration of some health parameters. By doing this, we can personalize machine learning models to improve prediction. And also for carers, we can present the aggregated data in a meaningful way, which is especially important if we have different like if one carer is providing care for several users. And also these systems can then act as the recommendation systems to give appropriate recommendations. So up to now, I was mostly talking about the very conceptual stage. So we have a system with different modules, something. But now I will talk about a device we actually implemented and put to testing with actual users. So this is a smartwatch personal assistant, which is based on a commercial device, an Android smartwatch, and we provided our dedicated software. The advantage of the smartwatch is that is a smartwatch. I mentioned earlier that some users are reluctant to start using the devices, especially if they're not something convenient, like if there is a pendant or something you put on your belt or these kind of things. The problems is that sometimes the elderly will feel stigmatized, like, oh, I'm old, so my family made me use this. I don't really want to use this. So there is a problem with adoption for sometimes. So instead, we are using a smartwatch, and smartwatch is a watch. So this is something that users are already used to. It's a watch. It has additional functions, and it looks nice in principle. It has a SIM card, so this means that it works indoor and outdoor, which is a benefit over the systems that are integrated in the living quarters. Some of the main functions of our system are automatic fall detection, manual SOS button, which connects to the call center. So this is for emergencies. There is physical activity monitoring module. And also we have location reporting in case of emergency and reminders such as take medications. Physical activity monitoring is a very interesting topic. There is a lot of research going on in this field. This is one of the highlights of our department. And in our system, it could be used either as an advanced fitness tracker or in combination with some health-related modules. For our particular smartwatch, we are just using the functionality to check if the user is active during the day or the user is in bed because he or she is sick. For activity monitoring, we are reliant on accelerometers and physiological signals that come from either smartphone or a wristband, in our case, a smartwatch. In order to train the models, we recorded a bunch of data in laboratory environment using volunteers performing different tasks. As you can see in the bottom, we have volunteers doing household tasks, outdoor activities, sports, and as you see, they're wearing masks. This is not because of the coronavirus emergency, because this was done a while ago. This is to detect, to measure the CO2 the users exhale, and this is a direct measurement for energy expenditure, and so to see how much energy the users use. So in brief, the physical activity monitoring algorithm first detects whether the data is coming from a smartphone or a smartwatch, and then in the case of the wristband, it's always located on the wrist. In case of a smartphone, it first figures out where on the body the phone is, either in the pocket or trouser pocket, or maybe breast pocket, or in the bag, or in the purse. Then it uses one of the dedicated models to see what kind of activity the user is performing. And then it's using a regression model based on the height and weight of the user to see how much is the energy expenditure. As mentioned, in our smartwatch system, the only use of this module is to detect whether the user is sick. So if the user is several days is very active and then maybe 2 days mostly staying in bed, there is an indication that the user may be sick. So it's good to check how they are doing. Now, the highlight of the smartwatch is the fall detection algorithm. The older the people are, the more likely is that if the fall occurs because of different reasons, that they should have some problems. This is especially important for people who are living alone at their homes. If they fall and if they cannot get up for several hours, they are in risk of developing serious health complications. Again, with the smartwatch, we are reliant on the accelerometer data on the wrist. In the graph, on the top graph, here you can see there is a typical fingerprint of a fall. So first the user is doing something, so there is some movement, there is a rapid change of movement, and then there is no movement. This indicates that the user is lying still, maybe unconscious, maybe cannot move. In order to detect only really problematic situations, we focus only on the activities when the user cannot move. So the user cannot manually call for help. If the user is still okay, then they can call for help by pressing the SOS button on the watch. So how to train the algorithm? We performed a series of falls and non-fall activities in laboratory environment. Of course, we did not use the elderly to perform the falls. We played this on ourselves. And there are different types of falls. It could be either walking and tripping, or collapsing because of some medical problem. It could be sitting on a chair and slowly falling down. It could be falling and trying to catch a table or some other object, but still falling. So there are really different fingerprints. Then we used different algorithms to classify these accelerometer signals, and there are different trade-offs. So if you are using neural networks, they're very nice in classification, but on the other hand, they're running all the time, so they consume much more power, and therefore they drain the battery. On the other hand, a rule-based system such as, okay, there is movement, and after all, there is no movement. This is much less reliable, because if you just put your watch on the desk, it will not move, but it's not a fall. But this kind of system is much faster, and it drains less battery. There are some other aspects in reducing the number of false alarms. So, for example, we can use the context, so what the user is doing before the fall. We can add additional sensors such as barometer or heart rate. So you can see, maybe it's counterintuitive that you can detect this with the smartphone or smartwatch sensor, but you can see that even for, let's say, for half a meter distance, these sensors are so sensitive that they can already detect this very nicely. And then we have collaborative learning, which is if the system has already recognized some pattern as characteristic fall, they can already added to their database, so these are easier to detect. Of course, we wanted to test how the users will react to this kind of smartwatch system. We had 150 users. Each of them was using the smartwatch up to 3 months. These people were living in nursing homes, and some people were living independently at home. Independent living here is very important. For example, for fall detection, if the user is afraid of falling, this is often one of the reasons why people would enter a nursing home, because they're afraid that something will happen to them and nobody will be able to help. If we use an electronic device such as our smartwatch to alleviate the fear of falling, of problems, then the users can live at home independently with a higher quality of life for many more years. So our users, they were all above 65 years old, but mostly they were around 80 years old. Some users had mild dementia, 2 users had late-stage dementia. We were using a project partner call center where the alarm calls redirected to, so there was always somebody online checking what is going on. Then in the pilot study, we wanted to see how the system is performing. So it's user acceptance, alarms, how they're using different interactions. Of course, before we started the pilot studies, we had workshops to teach the users how to handle the watch. And we wanted to teach also the staff at the nursing homes how to help with the basic functions. So this is my colleague explaining how the watch works to one of the users. And how the system performs. In total, we had about 700 alarms, and some of them were redirected to the call center. Some were canceled manually because this is the option. If there is an alarm, but it's a false alarm, then the user can cancel it because sometimes there is a false alarm. During the pilots, there were no actual cases of users falling unconscious, which in principle is good. We wouldn't want to have people falling unconscious just for the purpose of testing. We had 4 cases of undetected falls, but none of this was deemed critical. And we learned some unforeseen scenarios, which is really important, that reason that you're doing the actual testing with the users, because you cannot expect everything that may happen. One of the cases was a user in a wheelchair. So she was driving around in a wheelchair, and then whenever she bumped on some obstacle on the ground, the system recognized this as a fall because it was the pretty much identical fingerprint. So some sharp movement and then still, but this was because the user had their hand still on the wheelchair. Clearly, we did not expect this kind of situation before. We had roughly 1 false alarm per user per day, but the users in the evaluation part, they did not mind false alarms because they had the feeling that somebody is there actively taking care of them. So 1 false alarm per day sounds a reasonable compromise. We also noticed that initially the users often triggered alarms manually. Either they were testing the system, or they were demonstrating the system to their friends, or they just wanted to talk to the call operator for whatever reason. User habits. We found out that the users in nursing homes, they quickly gave up on the system because they already feel safe. They have people all the time around them that they're taking care. So these are not really the target demographics. On the other hand, users that were living independently, they embraced the system, and several users, but they used it in a way that was not exactly the same as we intended to. So another lesson to learn. Some of the users, they were only wearing the watch when they went out, but this was because they felt comfortable at home, but not as comfortable going out. Interesting, one of the users again started using his motorcycle, and one user again started to do some easy work in the forest. So because they felt more secure about it. With people with late stages of dementia, they could not remember how to press the button, and they even forgot to wear the watch. So again, this is not the target demographic. One of the key lessons that we learned is that we should introduce the technology to the users earlier, so that when the dementia sets on, that the users will be familiar with the devices, so that it will not be something completely new. In future, we plan to integrate additional modules, so to monitor stress, chronic diseases, maybe some other devices. We are working on different projects related to these kind of topics, but the question
Anton,
is,
please take your.
Yes,
Anton,
that's my last slide. That's my last slide.
Thank you.
Yes,
Thank you very much.
we want to improve the battery life. So this is our batteries was operating for 1 day, which is not as much as the users want. They wanted like 1 week or ideally 1 month, but the hardware is not there yet. Therefore, we want to keep the system able to adapt to different hardware. We can use it as a recommendation system, and we want to have a system that will grow with user. It will learn from the user habits, and it will be more and more appropriate when the time comes. With this, I would like to conclude my talk. I would like to thank my colleagues who participated in the project, and I'd like to thank you for your attention.
Thank you very much, Dr. Anton, for your wonderful explanation about the artificial intelligence of the smartwatch. Have the many applications. And now we are introducing the next speaker. It's my great honor. He is alumni of this university and eminent professor in IIT Roorkee. So Professor Chandra has a very big profile, so it will take a few minutes to introduce. So it's better we can take a look on the screen and we can understand. So he is a very eminent and excellent professor, and at present he is a professor at IIT Roorkee since April 2014. Before that, he was the assistant professor at the same institutes and assistant professor of the same institutes. So he worked earlier with the same department of physics, CCS University. So that's why it's our great honor to introduce Professor Chandra. Professor Chandra, you are most welcome, and please share your experience for our learning. Thank you very much, Professor Chandra.
Thank you, Professor Sharma, for this nice introduction. And first, I would like to thank all the organizers, Professor Birpal Singh and Professor Anil Kumar, Dr. Gautam, and other colleagues at the Department of Physics, and Professor Bimla, Y. Bimla from the Botany Department, my ex-colleague at CCS University Meerut. And this is my first experience to attend this webinar, and I'm grateful to Professor Birpal Singh and his team to have a new experience. So I would like to be within time, if so I can start. So I'm just sharing the screen now. Okay.
Sir, may I help you if there is any problem?
Yeah. Yes, you should help.
Yeah, you just have to go to share screen. There is a green button.
Yeah, I know. Yeah.
You just click on it. You will get a desktop symbol on the screen.
Yeah, desktop one. Yes.
The desktop one, you just click on that.
I clicked.
You will reach on the desktop.
It's not coming.
To the desktop.
This is asking open system preferences. Anil, it's not coming.
So your desktop is not coming?
Yes. This has put some question mark.
So you can try again. I don't know. It may be the problem of your system. I don't know why this is showing this.
So first you open your presentation on the desktop, and then you share. I think that will be easier.
This okay. This I have already opened it.
Now you share a screen from there.
You can you can see.
Yeah, I can see screen share is there. Yesterday I did all my different PC.
Now you share a screen and then you can see that particular document on the screen.
So you first unshare your screen. Let's start in the backward direction. You first unshare.
Okay, let me just.
Yeah, you unshare it. Then just minimize it and go. Basically, open your PPT on desktop.
That is open.
Open. Now you go to the share screen. Click on share screen.
Share screen where?
Downside, sir. Downside screen. Downside green color.
No, that is on your Zoom.
Yeah, on Zoom.
Yes, sir.
That is on Zoom.
But again, it shows desktop 1.
No other document.
No other documents like whiteboard, iPhone, Microsoft PowerPoint.
PowerPoint is there, so that you click. You click that PowerPoint.
But then it's asked me for system preferences and all those things, which is I think not required.
If you can see that PowerPoint, you click that PowerPoint only.
PowerPoint अगर आ रहा है तो उस पर आप क्लिक कर दीजिए. और अगर दिखाई दे रहा है स्क्रीन पर तो उस पर क्लिक कर दीजिए.
जी नहीं दिखा, ये नहीं हो रहा भाई. Basic, advanced files.
Click on share screen, then it will come.
Music, computer sound, second.
Yes. Using computer sound, you click here, sir. You click here.
But once I just click it, goes to allow Zoom to share your screen.
Yes. You allow.
Then this shows open system preferences.
Okay.
Sir, in between, if possible, then send the PPT to Professor Malik, sir, on email ID.
Yeah, I'm just. No.
We may take next speaker in between, Professor Gautam, if possible.
I think that will be better.
Yes, sir. So we may switch from next speaker. And sir, you please send your PPT to Professor Malik, and he will run just after 20 minutes. So, Dr. Malik,
yeah,
you please introduce next speaker, and let's start again.
Yeah, अभी आया शायद कुछ.
Okay. It's my great pleasure to introduce Dr. R.S. Davas, ex-scientist G and Deputy Director in charge of Regional Warming Center, RWC India, Radio and Atmospheric Sciences Division, National Physical Laboratory, New Delhi. He was scientist in NPL from 1981 to 2010. He did his I think he has worked at Kurukshetra University, Kurukshetra, India in 1980 or 1975. He won Liverpool Trust Visiting Fellow at the Department of Physics, University of Wales, and averaged with UK. He went to America and set up an ionospheric monitoring station at Indian Antarctica Station, Maitre. So I request Professor R.S. Davasji to please deliver his talk.
Thank you very much. First of, can you hear my?
Yeah, you sir, you are.
Yeah, we can hear, sir.
Okay. Actually, yes. First, I would like to thank the organizer and all the success for your meetings. And just like Professor Chandra also, it is my first presentation like this because I retired 10 years back almost. So, but Dr. Kavita is there. So she was my PhD student and she worked with me. So she asked me to give a presentation. And my topic of presentation. My presentation is on the space weather and its impact on human activity and space as well as on the ground. Can I start that by sharing this?
Yeah, sir, can you share or should I share?
Huh?
Yes,
Your slides? Or I should share.
Share my this. This is
just I am sharing.
Yes. Now I can go. Can you hear me as well? Hello?
Yeah.
Okay, thank you.
Yeah, we can listen, sir.
Yes, sir. Yes, sir. My topic is space weather, its impact on space, human activity in space as well on Earth, and the Sun-Earth connections. The presentation include what is the Sun-Earth connections, what is the space weather, and space weather effects, and lastly, the agency providing space weather information to the users.
Sir, may I interrupt you? Can you see the slides?
Yes, I can see my slides. I am using my.
On the screen.
Yeah, we can see, sir.
Okay.
So
Can you see my PowerPoint?
Yeah.
We can see, sir.
Okay, thank you.
Please start.
So this is, everybody know our solar systems, and here the Sun-Earth connection system. Everybody knows that Earth is a part of the extended atmosphere of the Sun, and Sun is a variable star. And varying in this, what is varying? Radiation is varying, solar wind is varying, energetic particle is varying. Question is, how and why does the Sun vary? How does the Sun respond? What are the impact on humanity? So why do we care about this, what is happening in the Sun and we are so far away? The question is, solar variability affect human technology, human in space, and terrestrial climate. Second is, sphere of the human environment continue to expand above and beyond our planet, increasing dependence on space-based systems, permanent presence of human in Earth orbit and beyond. So that is the reason human activity is expanding well beyond the surface of the Earth in the space. So this is the active Sun basically. This from the SOHO satellite from NASA. So it is just an active region, and if you see, just I'm escaping this. Actually, this is the active Sun, solar radiation and solar winds. Active regions and streamer let the solar wind, slow winds emerge from this and coronal produce the fast winds. This is the energy spectrum of the our solar system. And we see it extend from, in terms of energy, it extend from X-rays to extreme ultraviolet, violet, this visible lights and the infrared, and then again to radio waves and this. But 43% of the solar energy contained in the visible light. And here it is our atmosphere, right from this troposphere, tropopause, stratosphere, stratopause, mesosphere, the ionosphere and thermosphere, and this is magnetosphere. And this is the radiation coming from the Sun. If you see, right from X-rays to this. And you see on the ground, we are getting on the visible light as well as the infrared. Infrared and visible light is reaching, but rest of the radiation, X-rays, extreme ultraviolet, they are absorbed up to 100 kilometers or so. And others also absorbed in the atmosphere. And this extreme ultraviolet and this X-rays and other, they produce ionosphere, ionize the upper atmosphere, and which is called the ionosphere. I will talk about ionosphere as well. And infrared actually heat up the Earth's surface, which in turn, by conduction, heat of the atmosphere. What is space weather? Space weather originates on the sun. Space is filled with low energy charged particles, mainly electrons and protons, photon, electric and magnetic fields, dust and cosmic rays, because all the moving charged particles are always associated with the electric and magnetic field. Earth is immersed in the extended atmosphere of the suns, and extended atmosphere is called the solar winds. Solar winds are fully ionized gas that is literally explodes continuously from sun's corona. The density of charged particles and the fields in the solar winds are high enough to impact spacecraft, humans in space, and even human activity on Earth. There are changes in space environment, sometimes so violent and dramatic, we call them space weather. The solar winds hit the Earth at magnetic field because solar winds is mostly the charged particles, electrons, protons. It cannot easily penetrate into the Earth field as it is form of soft front and try to follow the around the sides of the magnetosphere. In doing so, it compresses and confines the magnetic field in the day side towards the sun, and this stretches out into the tail of night side, and the magnetic cavity formed by this way process is called the magnetosphere. In this process, I will show the picture. In this process, energy and charged particle are transferred from solar wind to the magnetosphere through the tail. This results in a rich variety of phenomena, which include the auroras, Van Allen radiation belts, and the giant magnetic storms, which produce changes in the ionosphere and can affect electric utility operation on the Earth, navigation and communication system. This is, I am showing a picture of the sun covered. If you cover the disk, how the energy is blasted in this. It is not actually, I have tried. It was a movie. So now actually how the sun energy is blasted out into space and subsequently trapped in the Earth magnetosphere. This gives the pictorial. It is not running.
Yeah, sir, you just asked me to move for the next slide. You cannot run it. Only I can run it.
Oh, it is not. It will not run.
Yeah, I can run it, but the control is in my hand right now, not in your hand. You ask me for the next slide, I will just move it.
Okay. You just please run. This will show the how the space weather.
Sir, is this slide okay?
This slide is okay, but previous slide, that is a movie.
Movie cannot be run because this is PDF.
This.
Oh, PDF cannot run movie. We don't have link basically.
Oh, you can't run movie.
We cannot run movie.
Actually, okay.
Because this is
that
PDF.
is a problem. Actually, it just like it goes, and this is the Earth, and this is magnetosphere. How it is? This is the night side. This is the day side. This is also, and the how when the space weather events from the sun's disturbance comes from, and how it is acting on the, how it is interacting with the Earth. This is basically the space weather geomagnetic storm. I would like to tell you something about this. When any events, space weather events occur, it compresses the initially, when it reaches around the magnetosphere, it compresses initially the day side of the magnetosphere, and initially you will feel the increase in the horizontal component of the magnetic field within few minutes all over the globe, and that is called the sudden storm commencement. And after that, it's from the tail side, energetic particles start trapping the magnetospheres, and it start gyrating along the magnetic field line from north pole to south and south to north, and that forms a ring current, just like this. This red is called the well band or the ring current. When a charged particles are trapped, mostly electron and proton, electron move along magnetic field lines in westward and electrons in eastward and proton in westward, and they form a electric current, ring current basically. And it is there different in different belts around the equator. The size of ring current or the size of radius of gyration of the electrons or proton around the globe is just like that. The center, the Earth comes in the center of this, and a ring current is just like a magnetic dipole at the center of the Earth. So it is center of the Earth. A magnetic dipole is set up, which is in the opposite direction to the magnetic dipole of the Earth. And when the this ring current start building up by accumulating more plasma inside this magnetosphere, then the net result is that horizontal magnetic field start decreasing for several hours till this event has gone away. So that is called the main phase of the storm, and it horizontal component of magnetic field reduces quite a bit. It depends on the intensity of this. Then it will start dying out, and it takes few days to reach to its normal value. That is called the recovery phase. That is how the magnetic it is called the magnetic storm, geomagnetic storm caused by the space weather event. And you see, you have observed one thing I wanted to point out, that in the polar region, by this space weather event, Earth magnetic field is changing very fast. And because of that, Earth is a good conductor, so it induces a very heavy current in the Earth itself. Millions of amperes of current is induced in the polar region in both sides, and which if in the northern side of the power grid line are there, that can damage that current damage the transformer, and that can be a complete blackout. I will show an example of that as well. And this is another is at the when they are trapped charged particle in the polar region, when they go around 80 kilometers or 100, some of the energy is lost to the background atomic oxygen or nitrogen like that, and they release in the form of this picture is aurora is from the Antarctica stations, our Indian Antarctica station. This both the picture when I visited there in 2009. So these are the space weather effects on different systems. They are shown in one picture itself. It shows charging of the satellites, solar cell damage, and the scintillations cause the navigation problem, communication problems, airline passenger radiation, enhanced radiation also, and in the satellite atmosphere drag is increased so that the orbit is changed, and similarly in the high latitude electric grid disruption takes place. Similarly, long distance HF communication, which is everywhere through the ionosphere, it is just transmitted from air, reflected back, and in one reflection from the ionosphere it can go up to 4,000 kilometers, and it again reflected back in around the globe, it goes like that. But during space weather event, it is a high enhanced D region ionization is produced because of X-rays, and it is not coming to Earth, so it is communication is basically disrupted. And this is the global picture of the how the effective dose of radiation take place around 12 kilometer height of the aircraft, which is passenger aircraft going. So most of the high radiation is there almost in the high latitude. The equator, it is very quietly significant less. So in GPS, ionospheric scintillation affects satellite communication, navigation, and during the space weather events, the enhanced ionization is produced, which produce irregularity and which disrupt the satellite satellite signals, and we call them scintillations. And that affect the satellite communication navigation system, including GPS. How defense communication and navigation system is affected because of this space weather event. You see the radar tracking of aircraft or the satellite communications at the fixed or the mobile this, and similarly the scintillation effect. All this defense communication navigation network is completely disrupted. And this is how the GPS system is affected by this, and GPS, you are not getting the correct GPS navigational information when there is this system is this space weather event is observed. Similarly, at the satellites, this solar winds and as well as the electronics is damaged because of the high energetic charge particle and other thing. And during space weather events, the atmosphere is heat up and it expand upward, and it produces enhanced drag on the satellites, especially low orbiting satellites. During a particular event, 1989 storm, which was very intense of the magnitude of sigma KP 9 plus. So during that period, thousands of satellites were lost, not able to trace them like that. And during that, there was power failure in Canada on that particular event, and it was remain almost for 7-8 hours completely over the entire Canada as well as over the US. And there was many complete blackout, equipment damage, tripping of the equipment like that. So if a country's power system goes away for 6-7 hours, you can believe everything becomes standstill. So that is the effect of space weather. But luckily, this event of such a magnitude, there is basically in sunspot cycle, is there 11-year sunspot cycle. In 11-year sunspot cycle, such type of event occurred only 6-7 in a 11-year period. So that is why, just like our earthquake, just like tsunami type, it was the magnitude of 9, but low level earthquake is always there. So at high latitude, there is a corrosion in the oil pipeline also observed. So I have summarized some of the specific effect of the space weather. HF communication, HF radio communication, it is a shortwave fade out. HF communication, degraded communication during atmospheric storm. VHF, UHF communication, unusual signal retardation, refraction in auroral zone, disruption of geomagnetic survey of the minerals, failure of the power transmission grid, especially in the high latitudes, increase of corrosion in long oil pipelines, increased drag on satellites, failure of satellites, electronics and control systems, problem of navigation system like GPS, hazards to manned space missions, hazards to passenger and crew member on high latitude aircraft flights, pointing and operational problem for radio telescope, widespread sightseeing of the aurora and stress related problem for the forecaster. So you can imagine how a single event can disrupt all the human activity on ground as well in space, or different types, whether it is a communication, navigation, or oil pipeline or power grid and the satellites tracking, other things. It can disrupt everything. So which are the agency providing space weather, just like IMD is providing weather information, and local weather affect the localized region of the earth, but the space weather affect the entire globe at a time. So there is an international agency which is called International Space Environment Services. International environment operate basically 12 regional warning centers globally, and these are the number of regional warning centers, and one is in India, which is operated by NPL from last 35 years to provide space weather information. And International Space Environment Services, ISS, what is their objective? ISS is a permanent service of the Federation of Astronomical and Geographical Data Analysis Services under the International Union of Radio Science. The mission of ISS is to encourage, facilitate near real-time international monitoring and prediction of the space environment by rapid exchange of space environment information and services to assist the user to reduce the impact of space weather on activity of human interest. Three basic functions accomplish the task of the ISS. First, the international RC-gram, a daily message is given to user agency, which include the current situation, all the information related to space weather, whether it is sunspot number or solar flux or solar wind speed, magnetic storm, other thing. Pre-exchange of space weather information forecast through its regional warning center. We are getting related information from the NOAA Boulder about the sun and the other things, but other magnetic and other data we are getting from the locally as well. The second, ISS prepare the international geophysical calendar each year. This calendar gives a lot of work days during which scientists are encouraged to carry out their experiment. And third, the monthly space warm bulletin summarize the status of the satellites in Earth orbit and in the interplanetary medium. Now, this is one Indian Regional Warning Center is operated by NPL from last 35 years. And I was in charge of that for more than 6-7 years. This is the website of our Regional Warning Center, NPL Regional Warning Center. It will give all the information about the introduction, daily messages, monthly geophysical bulletin, ionospheric data, ionospheric prediction models, solar activity predictions, and like that. So different to users. And this is how we are getting input from this regional warning, the geo alert, RC grams, daily solar magnetic IMF, CME, X-rays player data from Boulder we are getting on daily basis. Kodaikanal, Udaipur solar observatory give about the sunspot, solar flare, etc. IIG NJRI provides magnetic data and local K indices of the magnetic storm, ionospheric data from the chain of stations all over the country, right from equator to the Delhi and above. So this is the activity we are providing, and users for our users mostly ISRO, Indian Space Organization, all three wings of the defense, Air India, research organization, universities to get data and other things. So one of the important another application is that we are doing solar cycle predictions as well. 11-year solar cycle predictions, and we have predicted solar cycle 24th, which is currently in the minimum scale. And
sir, may I request to conclude?
Okay. Now, in 2005 or around that, Air India start operating a direct flight to US and the Canada, but they have to go through the polar region. Polar region means above 82 degree north. So by doing that, they save 2 to 3 hours of the aviation time. And you can imagine along with the time, how the energy conservation and other things. So it saves a lot of time as well as money. So that's why they are having direct flight. But there is a problem while going to they have interaction with us. We used to have meeting, what are the requirement, we used to give information to them, what are they wanted related to communications or space weather alert. But as you know, all the flights routes are always decided 10 to 20 hours before and is conveyed to everybody in the where it is going. But if any space weather information is space weather event observed, and they have to reroute because reroute the flight, then they have to take longer period, and they have to take another year. They have to go to other stations as well. So basically, what is loss of communication when there is space weather? Polar flights are affected in two ways: loss of communication, navigational problem, high dose of radiation to passenger as well. As I showed you the radiation chart on that high latitude is where ISS through this regional warning center should become the global public portal for aviation space weather education. RWC will deliver space weather information in an internationally agreed upon standard format defined by the aviation user requirement. RWC is providing space weather information to Air India in Delhi, Bombay, and US. JKF this. Now, as you know, by satellites we can get information about when it originates sun. We can get immediate information about the space weather event, but it takes 10 to 20 hours to reach the Earth. But we get
you to conclude, please.
In that, using that space, if we give the timely information about space weather event, preventive measures can be taken by the users agency. We are just we are giving to even Chandrayaan and daily. ISRO is using our data for launching of any satellites or what is the condition on that during that period, space weather condition like that. And you see, this is the to date. I told about sunspot cycles, 11-year sunspot cycle. There are to date 24 cycles is observed, and no cycle is similar to each other. All are magnitude. This is the magnitude. Duration is roughly 11 years, but 19 cycle was the highest so to date observed. So,
sir, may I request you to conclude, please?
This is just only 2 slides. Why we predict the solar cycle? For scientific research, spacecraft operations, satellite drag, planning of communication, estimation of number of flares, estimation of the disturbances, and amplitude cycle. What do we predict? Amplitude cycle prior to onset, variation of sunspot number within the cycle, length of the solar cycle, time of the solar maxima, time of the solar minima. That's why, and we use precursor method basically. And this is the solar cycle like this. We predicted 24 solar cycle this. So I'm just finishing this. We have set up a space weather monitoring station at Antarctica as well in 2008-9 beginning, and this is the NPL. This ionosphere station is there. So this was inaugurated by somebody. So thank you.
Thank you, sir. Thank you very much for so informative and important talk about the space science as well. Thank you very much.
Okay, thanks. Giving me opportunity to present, because it's a long time. I am not used to that, all these things. But anyway, I just try to give some information, maybe interesting to people. What is space weather?
It was very informative.
So, okay, thanks a lot, and I wish you all the best for your meetings and this. Okay.
Now our next speaker is Professor Chandradeep Tandon.
Okay.
Good afternoon.
Sir, 1 minute, sir. Sir, 1 minute. Just wait. I would like to share your slide. It is indeed my pleasure to introduce Professor Chandradeep Tandon, Dean Faculty of Bioscience and Biotechnology, Director, MIT Institute of Biotechnology, MIT University, Noida. He is the Dean since 2018 in the same department I introduced. He is Professor in Biotechnology from 2010. Hello. Can you hear me? Am I audible?
Yes, you are audible.
Okay. So he became professor in 2010, and in the Department of Biotechnology and Bioinformatics at GUIT Solan, he was and bias at Solan from 2007 to 2010, and he was assistant professor in the same department to 2007. He did his postdoctoral studies from University of Kansas School of Medicine, USA, and he did his PhD in 1998 from Punjab University. He has long list of awards and patents and papers. So I think I request Professor Tandon to deliver his talk. Thank you, sir.
Thank you. Thank you so much. I'm about to share my screen.
Yeah, you can share right now.
Is it visible?
Yeah, it is visible.
I put it
You
on
just go to the
slide.
slide.
I'm going to do that. I think here it is. Is it visible now?
Yes, sir, it is visible. It is all right.
Okay. At the outset, I would really like to thank the organizers of this very important topic. In fact, it's such an important topic in today's world, that is interdisciplinary science. And I really compliment Professor Birpal Singh and his team member, Professor Malik, and all others, and also Honorable Vice Chancellor for conducting such a nice conference. So I'm about to start. Okay. This is basically about what is interdisciplinary science. I will not go into, I promise I will be very particular when it comes to time. I won't take time allotted to me more than that. So it basically notes more than 2 or more fields. All over the world, innovations are taking place. The reason is fairly simple: good solutions to important areas. It's very difficult for science to progress if we rely just only on one component or one discipline. We have to come together to join our hands to see to it that we provide solutions to all the problems which are possible for the societal benefits. Here are the few important steps which are required for this. One is initiation, wherein you choose a real problem, identify 2 or more fields for interdisciplinary research, then planning it, study the real problem, develop a new fundamental or methodology. Then comes very important part of executing it. Develop and apply educational material, develop new technology, apply new technology, and comes the controlling part of it. Measure educational parameters, evaluate new technology, measure economics, and finally, it comes to the publication and also the part which is very important, its patent and its commercialization. Not able to go to the next slide. Dr. Malik?
Yeah, just click on the slide.
Yeah, I did. Okay.
Move it to the next slide.
I did, but I'm not able to go to the next slide. I'm trying various options.
That may be because your system.
Yeah, here it is. Here it is.
It may be because of internet or something like that.
Just a minute. I think this is the one. So these are the benefits of interdisciplinary research. Increased collaboration, which is need of the hour. Novel insights and perspective, reframing a problem, enhanced impact. You create an international caliber with high quality publications, patents, commercializations, increased funding opportunities. Today, in various funding agencies are always looking forward to those kind of projects which have this component of interdisciplinary sciences or transdisciplinary sciences in it, because it definitely would lead to development of newer skills and creation of high quality facilities. So these are the few of the disadvantages of interdisciplinary research, or you can say the challenges, technical difficulty, communication gap. Because if a person in the field of life science would like to interact with person in the field of chemistry, physics, or mathematics, in the beginning there is going to be a communication gap because we think from our own angle. So now I guess we have to come out of these boundaries or silos and interact with each other for better communication. Because if a physicist will look at a similar problem vis-a-vis chemist or a life scientist or a mathematician, their angle, their perspective is always going to be different. There could be few inflexibility issues or misunderstanding, but for success of science, for societal benefits, we need to get over these challenges. Yep. These are the few of the examples which I would like to give currently. I'm soon coming to very important topic of COVID-19 and the role of interdisciplinary sciences in that. But before that, these are the few very important examples which I would like to give. This is regarding, yes. When we talk of development of a new drug today, drug development. So most of the drugs which are coming, whether it's for cancer or it's for malaria, they're coming from plants. So here also you can see there is always a connection between various areas, whether it's life sciences, whether it's pharmacology, whether it's organic synthesis or computer modeling for in that case. Bioinformatics, we all know, which were also touched upon in the morning by Dr. Gupta. He mentioned about bioinformatics and biotechnology. Bioinformatics is nothing but it's a combination of computers and biology. Here also one can see, and bioinformatics recently with the last, also in the last few years have gained lots of importance and really has reduced the time for the drug development. Similarly, in this area also, agri-nanotechnology, interdisciplinary science plays very important role. This was the bioinformatics which I was talking about. Bioinformatics is not only the combination of computers and biology, but also a very good definition of bioinformatics is you develop a software to analyze and visualize various biomolecules or the data which is coming out of wet lab experiments. Coming to another very important field is biomaterial science. Here also the interplay of various disciplines, various fields are very important, whether it's tissue engineering or nanotechnology and biophysics. Biophysics, I would like to say, when we, in the morning, Professor Krishan Lal ji made a very nice presentation. So he's a person who has immense expertise in the field of X-ray crystallography. Here comes the role of physics. What is the role of now a biochemist or a life scientist or a biotechnologist? Biotechnologist will purify an enzyme. We all know what an enzyme is. So that enzyme purified first and later for its structure, decipherous structure, we got to know, we got to use a very powerful technique of X-ray crystallography. So one needs to have now a good connection, collaboration between a physicist and a life scientist so that science progresses. Okay, coming to now very important, or the one which has gripped the whole world, SARS-CoV-2 pandemic. SARS means severe acute respiratory syndrome. Currently, all over the world, around 4.3 million people are affected. And this is the data which I have taken. This is yesterday night. And I'm telling you, every day, there's going to be an increase in the people who are affected by coronavirus. And we all know the structure. Here is the structure of coronavirus. It looks like, we call it corona because it gives the appearance of a crown. And on the crown, one can see, it's like if I have to give you a simple example, it's like if you take a tennis ball and you put toothpicks on it. So those are the proteins, spike proteins, these red colored ones. Here is, I know this is a very heterogeneous audience. Still, I would like to give you general organization of. Don't worry about all these details, but the main important point is you must be hearing about another virus called MERS. MERS is a Middle East respiratory syndrome coronavirus. And if you see the S protein is present on, as I told you, it's like a toothpick on the ball, on a tennis ball, if you stick toothpicks. So this S protein, the structure is there, and it is one of the potential candidate for vaccine development. I would like to give you a very important data, which will of interest to everyone. We all know that against chickenpox, we have a vaccine. And let me tell you that took 28 years to develop vaccine. And the vaccine is called varicella vaccine. Similarly, for various cancers, HPV took 15 years. For diarrhea, the vaccination is also available currently in the market. It's called rotavirus vaccine against this. So this took again 15 years. Similarly, for it took 11 years. But for COVID, the target given is just 18 months. You can very well compare from 28 years for chickenpox to 18 months. And these 18 months are only possible if there is a good connection or a combination or a friendship or a marriage between various areas of the science. Otherwise, it's just impossible to do that. So here comes a very important, again, example of interdisciplinary area in the case of COVID-19. PPE, we all know PPE is personal protection equipment. If you see all these, the various areas of science have come together: vaccine discovery, repurposing of drugs of SCQ and remedy. These days is always, I guess, the person who are not in the field of biology, they also know about everyone is acquainted or apprised of these terms like SCQ is nothing but hydrochloroquine. This is a medicine which is being used for some other ailment, for malaria, but it seems to be very effective for preventing coronavirus. And similarly, another drug called Remdesivir, which is also antiviral drug. These drugs were not made actually to cure corona. But however, it has been found by scientists, by research, deep research, that these drugs also be used for this. And this particular area is called as repurposing. Repurposing means a drug which was made for some other purpose, but today it can be used for some other purpose. That's the word came, repurposing of drugs. So here comes a very important role of now artificial based systems for pandemic control. 4 or 5 days back, it came in the news that there's a medical college in Lucknow, King George Medical University. So they, along with another university, Abdul Kalam Technical University, they have made an AI-based app which can analyze the X-ray just by looking at the X-ray or the CT scan. This, and the help of AI and machine learning, one can come to know whether a person is virus or not. So here are a few of the other examples of interdisciplinary research in terms of COVID-19. Just like decoding the immune response to COVID-19. You take blood samples, do immunosequencing, machine learning, and research acceleration. You can say in each and every area, and the slide which I'm showing you, there is one, the theme is interdisciplinary research. Health vaccine and repurposed drugs, which I just spoke about, technology, which is AI, is artificial intelligence, robotics. More than 100 research groups are racing towards to get new vaccines and drugs against this new threat. And there is change in the speed. Original time was 10 years, 28 years versus 6 months to 1 year. Similarly, channelizing of resources and focus area, thinking differently, which I talked about, Remdesivir and SCQ, which is hydrochloroquine, which are drugs which can be repurposed. Here is a pictorial representation of what happens when a virus enters into cell. You must be hearing these days on television about a term called ACE2. That is angiotensin convertase enzyme, ACE2 receptors. So these are present, and these are the ones
COVID-19,
which help in entry of virus into the cell. And they say another data these is coming that men are more susceptible to COVID compared to women. So scientists are saying, as a hypothesis, maybe because the ACE is more prevalent in men compared to women. Perhaps that is one of the reasons for that. So this I've already spoken about repurposing of drugs. Here you can see this is chloroquine and hydroxychloroquine, which are used for malaria. So these days, lots of pharmaceutical companies, even Zydus Cadila and others, are into it, and this drug is being exported, is much in demand. Coming to the post-COVID, I'll be emphasizing on artificial intelligence. Today, artificial intelligence is playing an instrumental role when it comes to vaccine development. By help of artificial intelligence, one can easily identify the targets or the epitopes. These are nothing. It is something which I told you like a toothpick on the ball of a tennis. So if one knows by artificial intelligence which are the ones which could be the potential candidate for vaccines, so new algorithms can be designed based on that. It will help decrease the time of. Otherwise, if the techniques are not available today, artificial intelligence is not a technique used by life scientists. But today, to promote, to get benefits out of it, we need to collaborate. Here are a few other examples of interdisciplinary sciences. Ventilator design. Today, we all know that it's very, very important that ventilators should be made. And here is an example which was inspired by this fellow. He built his second and latest prototype under 3 hours using the same motor, drawers, gliders, and plywood materials and tools that could be found almost everywhere in the world. This was a result of a lot of conversation with doctors. Here again comes, interdisciplinary component, that a person talking to doctors and to see to it ventilator design. Similarly, coming to PPE manufacturing, respirators, eye protection, gloves, they all need interdisciplinary approach by engineers, by technicians, by doctors. So only together we can do that. This is a slide which shows how we can come together and come up with a solution for COVID-19. These are a few of the top stories which I just took a slide just 2 days back. Jubilant Life Sciences is doing efforts. There are lots of stories. I will not go deep into it about COVID-19. Here is what we at MIT University of Biotechnology are doing. We are also doing interdisciplinary research. This is a project funded by DST. This is one by DBT. Here also we are combining life sciences, biology with bioinformatics. Few of the other ICMR funded projects, which again depict the friendship between various interdisciplinary sciences. And thank you so much. Thanks a lot for hearing. Thank you.
Thank you, Professor Tandon, for giving so beautiful information about the coronavirus and its application, its issues, and how it is basically going to impact the society, and just showing the basically regarding how it is more basically dangerous for men than the women. Thank you very much.
Thank you so much. I appreciate it. Thank you.
Next speaker is Professor Kumar.
Yeah, I can hear.
सही बात है, पहला दिन है।
Yes, our next speaker is Professor Gagan Kumar. He is presently associate professor in the Department of Physics, Indian. Can you hear me? Am I audible?
Yes, yes. You're audible.
Okay. So, Dr. Gagan Kumar is associate professor in the Department of Physics, Indian Institute of Technology, Guwahati. He is associate professor in this department from 2018 to present. He was assistant professor in the same department from 2013 to 2018. Before that, he completed his PhD in probably in 2008 from IIT Delhi. Then he joined in 2008. He joined postdoctoral fellow in the Department of Electrical and Computer Engineering, University of Utah, Salt Lake City, USA, as a postdoctoral fellow. Then he joined as a project scientist and postdoctoral fellow. And then he also did, he was research associate in, let me check, in the Electronics and Applied Physics, University of Maryland, College Park, USA, from 2010 to 2013. So his area of research interest are terahertz, plasmonics, metamaterials, photonics, and waveguides. He has published more than 45 papers in very high repute international journals like Nature, Photonics, and all. So I request Professor Gagan to deliver his talk.
Yeah. Thank you, Professor Anil. I hope you are able to listen me.
Yeah.
Okay. Yeah, thank you for this introduction. Let me first share my screen from here. I hope you guys can see my screen. Okay, so yeah. Okay.
It is visible.
Just there is something popping out from here. I don't know how to remove this. So message is appearing all the time. Let me just see it if I can remove it. Something is here that is there on the screen. 1 minute, if I can remove that, let me see. Yeah, I hope now it's fine. Yeah, thanks for the introduction, Professor Anil Malik. And thank you very much for inviting me here. And I really appreciate you and the other organizers for organizing this event, especially in these tough times when we are all facing pandemic, and therefore keeping the motivation up for science and technology. So I'm gonna present my talk in the area of terahertz plasmonics. Terahertz is one of the frequency and plasmonics is one of the sub area of photonics. How do we combine both and how this can be used for making ultra high speed futuristic devices that can operate at truly high speeds, maybe many times faster than today what we have. So I'm here working, we have a lab here called Terahertz Photonics and Plasmonics Lab, where we are working on this work. Yeah, this is the outline of my talk. I will introduce what is terahertz, what are its application, how terahertz research has grown globally, what are the waveguides and what are the techniques that can be used for guiding the terahertz. And then one of the approach that is called plasmonics approach for making terahertz plasmonic waveguides. I will discuss about what is plasmonics and how it can be useful in making terahertz propagation over a metal surface and how they are useful in our life. I mean, especially in making devices. And then what are the applications of terahertz in terms of sensing or sensors? Then I will conclude. Terahertz is basically a narrow region between the microwave and infrared. Until a few years back, probably more than 10-15 years back, I would say, people, it used to be considered as a terahertz gap because of, we don't have much devices in this region. Even today, although there has been significant research in last couple of years. So this is a very narrow region and used to be neglected region, but it has a lot of potential that I will speak about. And in terms of frequency, if I say it, if 1 terahertz I am talking about 10 to the power 12 hertz, then it is 1 picosecond on time scale, and on energy it is very low, 4.1 milli electron volt, and that's why we can call it non-ionizing, and therefore it could be very useful in sensing where we don't want to cause any damage to the useful tissues. And in terms of typical time domain signal, this is how it looks like. And if I convert this time domain into frequency domain, then this single cycle pulse will give you broadband pulse, broadband spectrum, and this is how it looks like, just for the person who are new to it. And why it is so interesting, why we have so much interest in terahertz research. It has number of potential applications in different areas. For example, in medical applications, terahertz waves, as I said, they are low energy waves and they are considered to be safer than X-ray, and they have the potential to replace X-rays. They have some specific spectral signatures. If you are going to hit terahertz to maybe certain molecule, some substance, then substance may have some specific signatures. So it can do the imaging and also it can provide you content information. That way also is very useful. And some of the research that has been done in this area for the identification of tumor, dental science, as you can see here, if there are cancerous tissues at the surface, at the body skin, then this has been identified using the terahertz. Also in terms of imaging, these are a few of the differences, between the visible image by hitting the visible light and the terahertz. In terms of security screening, this is another area where terahertz has been examined a lot in last several years, and several big projects have been funded in this area, especially outside in US. The terahertz imaging is useful for screening of passengers for weapons at the airports. Now, at some of the strategic airports, we do have some sort of sub-millimeter or terahertz wave detectors, where they make you stand inside a chamber and they can find out, if you are having some concealed weapon or so. So that's why they are being used at some of the airports. And terahertz waves can create images of the concealed weapons. As you can see over here, a person is hiding a knife or maybe a weapon in concealed in the in clothes, and then they can be identified without touching the human person. And also you can see that terahertz is transparent to the sort of wood, sort of plastic, and therefore if knife is there hidden inside the underneath this shoe, then they can be, just without touching it, they can be find out. So terahertz waves may be more promising also, as they could sound an alarm. Like for example, TNT, RDX, they have some specific signatures in terahertz, and if a person is carrying those things and he's passing through a subway, then terahertz devices may be useful in tracing those items, and they can sound an alarm, without actually employing the security personnel over there. In the prevention of criminal offense, that is also useful. This is one of the pictures that I showing here. So a person outside here is having terahertz gun, and terahertz is transparent across the wall. If the wall is soft wall, basically, as they are mostly in the US, and they can easily target the person who is kidnapping. So it is said that a camera that can see through clothes, skin, and even walls without X-ray, and that is already under development, this would be one of the biggest technological breakthrough in the 20th century if we are able to develop it. This is another area where we can find terahertz waves as very useful. For example, you can see over here, we have a chocolate and it has glass particles or stones. And you can just do the terahertz scanning, and then it can tell you that it has sort of these unwanted particles. Similarly, this is another image where there is a metallic particle somewhere here inside the food material, and that can be identified by terahertz. So metal can easily be identified because they have a great reflectivity, high reflectivity at terahertz. But at the same time, if we have non-metallic contamination, terahertz spectroscopy can also find those kind of particles by a little bit of processing. So this is one of the area that terahertz is being explored for its potentials. We have been seeing 2G, 3G, 4G, and maybe 5G will come soon, and maybe 6G also will come in future, certainly. And people have been working on 6G also. So it is said that, when 6G generation or so, they will come, they will be operating at terahertz, because terahertz waves promises the transfer of signal at terabits per second. So what we need to do, that we have to develop devices that can carry signal, terahertz signal, sort of transistors, just like the electronics. So in that direction, one of the biggest need is to have waveguides, because waveguides are always useful, in terms of, making signal propagate from one place to another. And this is one of the area of research that we try to address here. But before I go to that part and discuss a little bit about how do we make devices that can propagate terahertz from one place to another, I would like to give flavor of terahertz research in recent times, how it has grown globally. So this is about the publications. As you can see that where publications used to be very less than maybe 200 to 50 in 2000. In 2018, every year we are finding in Web of Science more than 3,000 papers every year, and a lot of papers, in the interdisciplinary area, involving terahertz as being seen in the conferences. Wherever research is involved, ultimate outcome would also be seen in terms of the market value. So in that sense, if you see that, this is having a compound annual growth rate of 26%, and this is expected to be, by 2022, the total market value is around to be 2,800 crore. So this shows that, how terahertz research has globally grown. And this is just sort of giving you a flavor of the terahertz research that we are doing at IIT Guwahati. As I told you that terahertz have variety of applications. It is just like a tree. Terahertz technology is sort of a tree where we do have a lot of areas, whether interdisciplinary or specific to a particular domain. Research is going on, and largely we have been focusing here, or the publication that we have been making here, they are largely being focused in these areas: silicon-based terahertz devices, guided wave devices, terahertz photonic devices, and ultra-fast carrier dynamics. So now let me come to the waveguides. As I said that waveguides, or the means by which we can guide the wave, is very important for making networks, for making circuits, on-chip circuits, several, because without guiding the wave from one place to another, we cannot make futuristic devices. And there are a variety of waveguides available in different regimes of frequency regimes, like microwave and infrared. You must have seen rectangular waveguide, coax cable, optical waveguide, fibers, and all sorts of these waveguides. They are there in the terahertz. some research also, sorry, they are there in the other domains, but some research also has been done in terms of waveguides at terahertz, and some sort of like, dielectric fiber has been used, parallel plate waveguide has been used, photonic crystal fibers has been used. So they have been used and they have some specific use, for example, in terms of sensing, in terms of propagating signal from one place to another. But for making devices, for example, if you want to make a circuit that would operate at very high speed, then probably we would need, just like a chip, just like a breadboard, we may need that the wave could be confined on this. For example, this is a plain metal surface. It can be coupled to the surface and that can propagate to the other side in a highly confined manner. Just like we have a breadboard or sort of motherboard where one signal is propagating from one place to another. If we want to make devices that can work at terahertz, so we have to make some arrangement that can, propagate our terahertz in a highly confined manner along a particular path. And for making such kind of devices, I am here using the plasmonics approach. What is plasmonics for the beginners or for the new people? I would like to very briefly tell you what is plasmonics. Plasmonics is basically all about surface plasmons. All we know, surface waves, they have been there, from long back. Even the radio wave communication that has been happening across, even a curved Earth's surface and propagate to a long distance considered to be surface wave. But when we are calling surface plasmons, means we are propagating surface waves along the plasma. Here, metal is a plasma, and surface wave means they should be always confined to the surface. For example, you see this animation where we have a wave that is confined to the surface and propagate to the other side without leaking into the outer region. What is the advantage of that? Advantage of that is that we will have a huge field at the interface, metal or dielectric or any conductor or dielectric. If we have a huge field at the interface, then we can do variety of things. We can do sensing, we can do maybe sort of non-linear things, or probably, we can do material ablation. There are a variety of applications we can do. And briefly, I'm not going how do we get this thing. If interested, we can follow my publications. But just to give you a flavor, what extra thing this surface plasmon wave or surface wave at the plasmas can do, that if I somehow solve the Maxwell's equation and find out that, what is dispersion, so what will I get ultimately? I will get that this is the dispersion relation, and plotting frequency with wave number, what I will get is that this is bending away from the light line, means my wave number is bigger than the light line. What does that mean? It means that if I can somehow come with a laser light, I can convert into surface plasma wave, then I am going to bring down its wavelength. Wave number is bigger, so wavelength is much smaller. So means ultimately I'll be working with smaller size wavelength as compared to the light line. This means that we are able to overcome the diffraction limit. You guys know that, in terms of making devices, Morse has said that, a limit will reach, because we have a diffraction limit, a limit will reach where further miniaturization or further enhancement of the speed is not possible. But if we do convert our light wave into the surface plasma wave, then probably we can make even further smaller size devices for future. And now the question comes that how do we get these waves? Because by hitting the light from the top to the surface, can we get surface plasma waves? No. Because as I said that this has bigger wave number, means we do have to have special arrangement in terms of coupling our free space light to the surface. And there are a couple of techniques have been used in the past. I'm not going to discuss them in detail. They are available on the internet. They are Craftsman and auto configuration, very standard configurations. But since I am more interested in guiding terahertz because they provide me more high speed, so now I have to worry that how do I propagate surface wave using terahertz or terahertz surface wave, because at metals at terahertz behave like perfect conductors. For this purpose, as you can see here, when we come up with a terahertz wave, then it will show an asymptotic behavior, and therefore it cannot lead to the confinement. So there was one pioneer paper by Sir Pendry in 2004. He had told that if we can somehow corrugate our metal surface, then it can provide us required skin depth, because at terahertz, it does not provide skin depth, but if we make it corrugated in a periodic fashion, then it will sort of provide some skin depth, and its dispersion relation exactly looks like what we get in the optical region. Means we can mimic the surface plasmon behavior using these metals at terahertz frequencies. Now, how do we use this kind of assembly of these corrugations to make the waveguide devices? You see that this is a metal plate and we have corrugated it in a one-dimensional fashion, and somehow we are coupling this light. For coupling, we are using the semicircular groove. So what we do that, we come with a broadband light. Broadband means several frequencies or big band of frequencies, broadband light, and we are hitting, as you can see from here, to this coupling groove, and it will couple the light to these corrugations. And once it is coupled to the surface plasmons, then they will keep on propagating to the other side, and they can be detected by some means. This is electro-optic sampling. Again, this is more technical. I'm not going to discuss that, but certainly by some detection method, they can be detected. And they are only confined to the surface. Okay, so this is one of the bigger view that we see here for propagating the signal to the other side. And because we are right now here studying the waveguide, so when I say the waveguide, it should have a confinement. There are some spectrometers at terahertz available, but for making the waveguide measurements, we have to have some different arrangement. And this was one of the arrangement that we had worked upon in my postdoc, where we brought the light from the top using all sort of high power femtosecond lasers. This is a small setup that we build a box in which we build our setup, because it is in a box, because we want to protect it from air, because air absorbs the terahertz, and we were able to detect the surface plasmon terahertz signal on the other side. And the advantage of this spectroscopy technique is that, unlike FTIR or other techniques, is that in terahertz spectrometer we do measure the amplitude as well as phase information. What does that mean? Is that we are knowing that what is the absorption feature, just like FTIR, but when we measure the phase information, because we here measure the electric field, then we can also know the content like refractive index, or the real or imaginary dielectric constant, and this can provide a lot of information about about the material. So now again, as I said earlier, that when we couple the broadband signal, this is the broadband signal, as you can see here, and when we couple this broadband signal, then it will propagate to the other side. And this waveguide was something like 10 centimeter long. And when we placed the detector on the other side, then we found that only some specific modes were propagating. And how do we know that they are modes? When we are calling them modes, means those were some specific frequencies that were propagating. One is this one, one is this one, one is this one. We did some more analysis, theoretical as well as through simulation. We found that their field patterns are quite different, and we called them modes. Means if you are hitting this waveguide, planar waveguide, okay, and with some broadband signal, and it is propagating with some well-confined modes to the other side. For example, this was the waveguide. This is how it was propagating to the other side. And when I'm saying that this is highly confined, means we also check that by placing the detector at different positions, how the field was high here, maybe low here, here. How does it propagate? Means how the loss of the waveguide is. Also, does it really remain confined? Because this is basically a confinement in the transverse direction over here. Okay. And then this is the confinement in the lateral direction, that is away from the surface. If I am calling it a highly confined mode, means that it should remain confined. My signal that is propagating along this pattern should remain confined in all the dimensions, in the transverse direction, in the lateral direction, and in the direction of propagation. The signal loss should be very, very less. And then we also sort of made some bands and splitters. Here you can get a very good flavor. So we have something like in the beginning, we have a signal that is coupled to these kind of corrugations. And as we are bending these corrugations, you can see that my signal bent. If I bend it in some other direction, then it will bend in the other direction. If I make it straight, then it will propagate in the same direction. So means that, by making these corrugations, we can generate terahertz surface plasmons, which can be confined to a particular direction, and that confinement direction we can define. This is one of the other research area that we have recently addressed here, since we had been making these devices. So what we thought of that, can it work as a waveguide sensor, terahertz sensor? So since we had these waveguides, what we did that we filled them with these analyte, and when the analyte was filled, we found that whatever the mode was propagating on the other side, for example, this is one red color mode, then by putting analyte of different refractive index, we found that this frequency was shifting. And we found that with refractive index over here in the lower graph, we found that this based upon what the shift is with the refractive index, basically one can use this technique for detecting the analyte. So this is another sort of application of the plasmonic waveguide. So in summary, so by coupling terahertz incident waves into surface plasma waves, or basically I can say terahertz plasmonics, it can lead to highly confined propagation. These are some numbers, of the modes to the other side on a planar surface that can be useful for making chips and networks or waveguide system for next generation ultra high speed communication devices. Okay, and with the miniaturized size, because we are using the plasmonics approach, and also waveguide approach can be used to build thin film terahertz sensors with greater sensitivity. Why do I say greater sensitivity? Because we have the analyte interacting with the surface wave for several order of wavelengths. Unlike the direct transmission approach, we have the wave will come, interact with the analyte and detect it on the other side. So that way also this could be very sensitive for next generation, very high sensitive sensors. And as I said that these kind of planar waveguide structures could be useful in next generation ultra high speed devices. Therefore now next we need to come up with the components, just like transistors, just like we have in the electronics transistors, we can come up with plasmonsters, something like that, or something devices that will make use of the terahertz surface plasmons. Here, this is just a picture of my lab, and this is my group, just to give you a flavor. We are currently 5 members, 3 more members that we have are working for BSc, their projects. And tomorrow we are organizing here International Day of Light. Tomorrow we have International Day of Light, and we are celebrating here in the Department of Physics. And if you wish to join, it will be on the Google Meet. And you can visit our website for more details about the speakers and how to join. Thank you very much. And thank you again for giving me the time to present here and keeping, the motivation up for all the science and technology society in this tough time, basically owing to pandemic. Thank you, Professor Malik and organizers.
Thank you, Gagan. Thank you very much. It was very informative, introductory, and explanatory lecture about terahertz. It is also basically my area of research too. So that's why it is more important for me to terahertz and then applications of terahertz. It is really very interesting area these days. And what is role of plasmonics here? How can we enhance the sensitivity of terahertz devices using this technique? Then waveguides. Waveguides are very good, very useful for communication purpose. And then terahertz sensors, which are detect the shift in frequency. So it was very nice, very informative, and very good lecture. Thank you, Gagan. Thank you for accepting our invitation for very short.
Thank you very much. In fact, giving me the chance. And if anyone wish to get more information, we have a website, and also, I'm open for more discussion later on whenever any audience want.
Let me add one more sentence here. Terahertz science is basically very new science. In fact, and very few people are working in India on terahertz science. So those who want to enter in research in this area can contact to me and to Professor Gagan. It is a very good area. It has huge applications, enormous applications in the field of medical sciences, in the field of communication, in the field of remote science. So I think there is no area where terahertz is untouched right now.
Just to add one more line, we have a few openings for in our group for the internship. We can pay them for the internship. And also in the coming month, my PhD position is also available in June, July. But internship, if you are willing to send for 1 month, 2 months or so, then we will be happy to pay to the students if they want to get a flavor for all the audience. Thank you.
Thank you, Gagan. Thank you. So nice of you. Thank you very much.
Thank you.
Gagan, can you stop sharing your slide?
Yeah, I'm doing that. Yeah, just wait. Yeah.
Thank you very much. So now is the time for lunch, and we will reassemble at 3:30 for oral presentation. So those who has to present their oral present or have to give oral presentations, please reassemble at 3:30. Gautam? Dr. Gautam, can you hear me?
Yeah, yes, sir.
Yes, you have something to announce?
No, we're just going to lunch and we will back in our presentation.
Thank you.
And thereafter there will be a poster presentation.
You just tell about the link for poster presentation.
We will tell the link after the poster session. I will discuss to you later. Sure.
Thank you, everybody. Please reassemble at 3:30.
Yes, sir. Thank you. Thank you.